called global secondary indices. Let's look at how this works. Let's start with our normal container, the order container. As we mentioned earlier, it is partitioned by order ID, but it contains other JSON properties like customer ID. Now I define a new index container called customer orders, which is defined by a covering query shown here, select star from order, and a partition key. In this case, the partition key will be customer ID. Once I set this up, the customer ID will get live updates from the order via the full fidelity change feed, filtered by the covering queries seen below. Now, the customer orders container is called an index container. It's a read-only container. Apps cannot write to it, but writes can only come to it through the order container. And the beauty of this is a user can query the order container by order ID or against the customer orders container by customer ID. At both times, they are point queries, so they're cheap and fast. We avoid expensive cross-partition queries. Now that we've covered three of the main core pieces of functionality, let's talk about some optimizations in terms of latency and cost. There are three types of optimizations worth considering. We've already talked about the first one, which is to use a GSI. The second one is about partition scoping. First of all, what is partition scoping? Let's look at an example. Let's pretend that we have a user collection. That user collection stores documents, as shown here, user.json, and it's backed by a POJO class, shown here on the right, user.java. If I want to select like George Jetson from the database, I would provide a point query as shown here, select star from C, where c.id equals a bind param. There's one problem here. Every time I issue this query, there's an extra round trip that is used to parse the query and generate a query plan. If I execute this query every time if I use this code every time I execute the query will incur an extra round trip. But if I add the line shown here where I set the partition key on the Cosmos query request options, then the first time will be the only time that the query will generate a plan, and then it will be cached in whichever pod this application is running in, so that subsequent queries avoid an unnecessary round trip, and this can cut your point query latency by up to 50%. Last but not least, let's talk about payload size reductions. What I'm showing here is how RU costs vary as a function of the payload size and also based on the type of operation you're doing. As you see, as I go to larger and larger documents in the payload, the cost in terms of RUs increase, but they increase more dramatically for point reads. Point reads double in cost as a power of 2 of the document size. However, you'll notice that under 32 KB, it's cheaper than point queries. But because point queries have a very flat slope, over time, they end up costing less. So let's look at the example from before where we had an order ID with in model 1 with its array of line items. In this case, let's pretend I had 100 items in my cart when I checked out. If I want to save space, what I can do is compress the order line items using an algorithm like Z standard and base64 encode it so that I can store it as a string field, a string property. I've also shown a property called compression, which has a bunch of metadata, but that is not needed. Assuming we kept that metadata, what will happen if we use Z standard with its default compression level of 3, we can save 75% of space. And this will result in almost up to 75% in RU reduction. At this point, I'm at the end of my talk, and I want to thank the following people for their guidance and support. Thank you.
Hello, everyone. My name is Chander Dal, and I'm the CEO of Kasten. an elite AI consulting firm delivering high-impact, enterprise-grade solutions, including custom-built AI chatbots and advanced automation systems tailored to complex business needs. Today, we're going to talk about one of the most important concepts, which is agent memory. And by the way, it's the same for your chatbots. And why is agent memory so important and how to get it done right? So today I'm going to show you 4 strategies, starting from a strategy in which we talk directly to LLMs. And let's not forget, LLMs are stateless and they do not have any memory whatsoever. And then we'll use the other 3 strategies, sliding window, hierarchical, and entity graph. And one of them will lead to the highest precision, and that will be the high precision or recall winner. However, that doesn't always mean that it's going to be 100% recall with that particular strategy. We'll show you different use cases, and from that, you can decide what's the best for your particular use case. We will start with 60 seed messages. And the reason we chose 60 seed messages is we saw that in a lot of companies, when they do AI testing, especially on their chatbots, a lot of times they go up to 10 to 15 conversations only. And guess what? All the 3 strategies provide 100% recall up to 30 turns in most cases. And that's why by the time you end up in production, you may not even know that you have less than 100% recall. And that's a big no-no. We also will show you 10 recall questions. And the first 5 questions are really easy. And all the 3 strategies get them right. However, the next 6 questions are more nuanced. And that shows how you need to change your testing strategies, especially if you're leaning more towards the easier questions during your AI POCs. So let's have some fun and define the problem. If you started working like me before ChatGPT was launched on AI applications, you may have noticed the context limits were really small. The token window limit would be the most important thing before you even started creating these applications. You would notice right up front that these LLMs actually are stateless. So after ChatGPT was launched, a lot of people assumed that LLMs are actually stateful. And in some cases, they even thought that it has a memory. A lot of that has to be done by engineers like you and I. You might have heard of the famous quote, "I told you my name, my budget, my team, my deadlines, and you forgot everything." And that is why memory happens to be the most important conversation in enterprise applications worldwide. So now that we know that LLMs have this problem, that they are stateless, and every API call starts from scratch, how do we solve this problem? Well, very easy. We can send the full conversation history every single time. Yes, except we know all LLMs have a limit. All right, then maybe you can just summarize it. Let's try it out. In case you send the entire conversation, and let's assume that's within the limit an LLM expects, in that case, you're still having costs that are going to explode. You're also going to slow down the LLM. What if you start summarizing parts of it? In that case, you still have that issue that you may be losing some context, maybe some fact, anything real world that you really care about that got compressed, because all summarizations have a compression problem. And then finally, users will have to repeat themselves quite a bit. So why does memory matter? One of the most important things to remember is that more than 70% of enterprise projects will require multi-turn agents. And the number one gap cited by developers happens to be long-term context. And by the way, if you go with the LLM alone, which really has no memory, and you go with the best memory strategy we're going to compare today, you may be looking at a 20x token cost difference between these strategies. And that's why memory isn't just a feature checkbox, it's an architectural decision that determines cost, recall quality, and user experience. So the first strategy happens to be sliding window, which keeps your recent messages and then summarizes the messages before it. An analogy would be a security camera that keeps the last 8 hours of footage and then writes a one-page summary of everything before that. That's really easy to implement, and that's a strength. And it's also going to have a low token cost. In this case, roughly 1100 tokens. And it's great for short conversations, especially less than 30 turns. And this is something to keep in mind. Just because it's great for that particular use case does not mean it's going to be great for another use case where we actually require a real world fact, even the one that was 100 turns ago or 1,000 turns ago. In that particular case, recall is going to be lower. And in today's demo, it's got about a 60% recall. Let's not forget, you will have 100% recall if it is less than 30 turns. So remember, it isn't about the strategy, it's more about the use case. And based on that use case, we need to pick the strategy. Strategy 2, hierarchical memory. Think of this as 3 different tiers. The first tier being hot. For example, a company's knowledge management system will have your team's messages as your first tier. And that's part of your conversation, and you want to send them as it is, uncompressed. Number 2 is your weekly meeting notes. And let's call that tier 2, and kind of compressed summaries, because tier 2, not as important as tier 1. And then finally, the least used out of the 3, which could be your company wiki. And those are extracted facts in your long-term storage. So better recall than sliding window. And of course, it can do better than it, but not as good as something that will always present the right fact every single time. Because tier 3, as you can notice, it will miss on certain facts here or there. Finally, we got entity graph. And I love this analogy. It's like a detective's case board where you have all these different facts, and then you got linkages between them, right as every single card with connections between them. And that's entity graph. So what does it store? It stores all the entities, anything real world, a name, organization, anything real world, any entity that is real world gets stored. Facts, these are key value pairs for that particular entity, and you can have any amount of these. And finally, embeddings. You may have heard of vectors, and vector databases got created simply because of these LLMs wanting to search, basically do semantic search on your data and get you that particular retrieval. Now, in this case, what I love about Cosmos DB is that you have the native vector search inside Azure Cosmos DB. And then finally, relationships, which are connections between entities. Now, why do you get 100% recall in this particular case? I mean, the reason is simple because we don't really have any compression. We're doing the vector search, we're getting those entities, and those entities have the facts, and we can get all of that back. So in this particular case, for this particular data set, we are able to get 100% recall, except we're also using average 1660 tokens. That's pretty much 50% more than the first strategy, that's sliding window. And remember, that's cost. So that's another consideration. So even though I would say there are 4 approaches, you might have noticed I start with 0. Why is that? That's because I'm an engineer, and as engineers, we use arrays and we start with 0. That's not the case. I really don't think it's an apples to apples comparison because LLMs really have no memory, no context of what you're trying to do unless you provide it. So for that reason, I don't think it's a good comparison, but I still want you to see that you may be able to get 92 tokens, but you got a 0% recall. However, the other 3 strategies, very important. As you can see, we go from 1100 tokens all the way to 1660. And in this particular scenario, you go from 60% recall to 100% recall at a 1.5 times the token limit. But here's what I love about Azure Cosmos DB. Same database, same SDK, same partition key, different recall guarantees, and I can use all these three strategies at the same exact time. So that leads me to why Azure Cosmos DB for agent memory. Well, that's because we are in Azure Cosmos DB conference. That's not the case. It's really because at the end of the day, all my data is in Azure Cosmos DB. And by the way, for someone like me who's been working on document DB, that was, I think, was 2016 onwards, I started working on it. And then it became Azure Cosmos DB. And I know we now have another document DB, which is a little different than that document DB that was there long back. My data and my client's data lives on Azure Cosmos DB. It used to be a big problem to now have another vector storage, a completely new database just for dealing with vectors. Well, no, not anymore. We can actually have that data, your embeddings, your vectors live right alongside your data. I don't actually need to have another native vector search database. The schema is flexible, and we talked about that. I love the session isolation. My partition key in this case happens to be session ID, so I have 0 cross-partition queries. And then finally, for this demo, I'm not worried about global scale at all because all we have is about 60 different messages. But once I go into production, I don't have to worry about global scale because now I can scale as much as Azure Cosmos DB would allow me, which is literally all over the world. And that's why Azure Cosmos DB. So let's talk about the benchmark where we have about 10 recall questions. We got the core questions, basic recall. Why do we have that? A lot of times what we noticed was all these POCs that people were doing had a bunch of the same kind of questions. And a lot of times those questions were created by AI itself. Well, but it was also 100% recall based on questions that probably don't understand how these strategies actually work. So what you'll notice is 100% recall for all three strategies for the core questions. We also notice that every single data set is different. We work in healthcare, manufacturing, finance, fintech, tech, pretty much name any major domain. And all these bigger corporations worldwide in those domains have very nuanced data. That's why I wanted to show you how much difference gets made in just 5 questions the moment you start asking nuanced questions on that particular data and how the misses happen. So for example, in this case, sliding window only gets 1 out of those 5 correct. So your recall happens to be only 20%. But if you have the right use case, sliding window could be at 100%. And that's why it gets confusing. Before we do the demo, I would like for you to ask yourself which strategy is going to remember a URL mentioned once 40 plus turns ago. And I hope you get the answer right. Let's dive into the demo. As you can see here, I've got 2 providers. Here's Azure OpenAI, and you can also click OpenAI. It'll work with both the keys. So if you have Azure OpenAI, assuming you have the same exact keys for whatever model you're trying to use. Here's 2 different demos. One is Kasten and another one is default. And remember, they're both fake data. So please feel free to use your own data. I'm not going to ask anything from the direct LLM because at the end of the day, we're not going to get any answers. Now we're going to compare the other 3 strategies, which is sliding window, hierarchical, and entity graph. On the right-hand side, it's just a way to see what the results are and what to expect. So let's ask the first question and see what it does. While it's answering the question, I just want to show you that all 3 of these are going to pass. So this is actually a really easy question. No problem whatsoever. All of these strategies will get you the same exact answer, which is Kasten offerings are consulting, training, and recruiting. Same exact answer, pretty quick. And you'll notice hierarchical was extremely fast, but entity graph is actually slower. Still gets you the same 3 answers. So now I'm going to skip the next 4 questions and go to number 6. The reason is because the next 4 questions, we're going to get the same result from all the strategies. So here's a result which says about us and contact us. All right. So let's go to round number 6 and open this. And you notice it's missing consulting. Let's go to hierarchical. Run this round. It's got about us and it's got consulting, which is true. And that's exactly what we were expecting on the right-hand side. Here's your entity graph. It's got about us and it's got consulting. It's got both the answers correct. All right. So now let's go back to sliding window and we're going to go to number 7. And here we're going to open the round and see what we were expecting. All right. It's got about, it's got web P, it's missing products, and it's also missing from our stored graph context, which is true. Let's go to hierarchical. And as you can see, it's got pretty much everything except it's still missing products and also missing from our stored graph context. Let's go to entity graph. And you may have noticed entity graph is actually slower. So that's another thing to keep in mind is what your use case is. So you've got actually everything. You got products, you've got the about gender doll, you've got the web P. It's actually perfect. And it also says from our stored graph context. That's pretty amazing. Let's go back to the 8th round. I'm going to pass because they all get the training URL. So it's the same exact answer for all 3 of them. And now let's just show one more. And let me go back to sliding window. Let's go to number 9. Very quick. And it's got something. Let's see what it is. Okay, so it's actually missing presentations, which is true. Let's go to hierarchical. It's got presentations. So hierarchical's got all of those. And same with entity graph. And in the 10th round, it's a very nuanced round. All that is getting wrong is not the response. They have all the responses correct, both of them, except they're missing from our stored graph context. All right. So how many of you got that right? I hope it's all of you. So what you just saw was direct LLM has no prior context. We didn't do that part of the demo, but the idea is you're not going to get any response if the LLM does not have that data unless you fine-tune it to have that data. Whereas sliding window, the first 5 questions correct. The next 6, it only got 1 right, which is the 8th one, which we didn't run, but it was really easy and it was going to run. Now you've got hierarchical, which was 3 out of 10, which means in this case about 8 out of 10. So you notice what's happening. Even though it was 3 out of 5, sorry, not 3 out of 10, we had the first 5 really easy questions, and you may think you have an 80% recall where all you had was a 60% recall because 3 out of 5 were correct. An entity graph in all the cases was 10 out of 10. Now, one of the things I want you to remember is that if you had a sliding window, which never requires you to go beyond 30 turns, you would have a 100% recall in sliding window. So it's really not the recall as much as it is the combination of your strategy, your use case, and your data done right. So here's your scorecard. If you remove the blue, which is the first 5 questions, sliding window is only 1 question. That's 20% recall. Hierarchical, 3 out of 5. That's 60% recall. In entity graph, 10 out of 10. So, and 5 out of 5 and 5 out of 5. So that's 100% recall. Cost versus recall, the trade-off is right here. And it's important because if your use case is literally less than 30 turns, you're better off going with sliding window because the cost is 1.5 times more in terms of entity graph. You're using the least amount of tokens. You're hoping you get the response also faster. So that's another cost to keep in mind is performance cost. Otherwise, if you really care about higher recall, well, in that particular scenario, entity graph would be a much better deal altogether. So an easy way to look at this would be sliding window for less than 30 turns, supports the chat, recent context, hierarchical, about 30 to 100 turns. And again, this is more, it'll depend on your data, but let's just say ballpark, that's what you're looking for, especially if you're using it for planning or consulting, and you have to have some key facts. And then entity graph, for example, you have your CRM bot or something where every fact matters. Like you don't want a response with a financial number that's actually not correct, and it can also scale do way more than 100 terms, because at the end of the day, you're really getting the fact correctly. So again, you can start with one. You can also upgrade later. You can also do a hybrid, which is also not a bad idea. And in some cases, you can have a combination of, let's say, a sliding window as well as entity graph. For 90% of your cases, you may have sliding window, especially for less than 30 turns. And then you can, go to entity graph whenever there's a premium use case behind it. So again, memory is a spectrum, and you need to choose by recall, not by hype. And you got to remember what's your use case and what your data is like. What we covered was the problem, which is LLMs are stateless. They have no memory. Then we really covered the baseline plus the next three strategies. And then the architecture, which was really easy, by the way. You must be wondering why 5 Cosmos containers. To remember, for entity graph, you will have different containers per entity graph. And that's not at all a bad idea. In this particular case, that's what we did that. You can do it in multiple different ways, but for that reason, we had more than just one container. And then you've got the live demo, which had 10 recall questions. Then you had the evidence, which was 100% recall in terms of entity graph. And then the decision, which isn't really about the recall numbers that we shared here, but a lot more than that. And we discussed every single of those. Now, just remember, this is not production data. And this is literally fake data, but this is also not production level code. However, it's a good POC if you want to run, and that's your barcode. If you click that barcode, it will take you to this blog post that explains the nuances, how the decisions were made, and it also explains to you the different parts of the code. I just want to show you this real quick. For your code to remember, here's your direct LLM. And if you're a .NET developer, you can look at the right-hand side of the code. And if you're a Python developer, you can look at the left-hand side of the code. Direct LLM, it's literally sending the system prompt and then creating the message chain and then making a call. It's very simple. That's how you've been making all your calls so far. Next is sliding window. And as you can see here, we have the summary for anything beyond 30 messages, and then just 30 messages where everything is uncompressed and it's part of the context we're sending to the LLM. And as you can see here, the window size is 30. And this is your 1 hour, which is, we just chose that time to live, and that can change for whatever you're trying to do. And then you've got the hierarchical memory. And here is where all your tiers are. And as you can see, here's your tier 1 size, your tier 2 block, and the max tier. Same for both Python as well as .NET. And then you've got the entity graph. This is actually really easy to produce because your entities and your embeddings are living together. So one thing to remember is that this is exactly how we anyways code when we are doing programming, because we have the same exact objects. Now we just have a way to retrieve those objects and then make it part of your LLM answer by giving it the context which it needs to give you the response. And finally, here's your read path on entity graph. And this is just a small blog post that I prepared only for the demo. However, a lot more detailed blog post is right here. And if you want to do a more involved code walkthrough, you can click that link and it goes through a lot more than what I just shared. So let's not forget, here's the link to that. And I hope you take advantage of it. Let me know if you have any feedback for me. I had a blast and hope you have a blast coding and using this in your applications. Thank you for having me. Have a great day and a great rest of the conference.
Welcome back. Thank you so much to our speakers. I believe that was Sid and Chander. They were both great, right?
Yeah, honestly, that was a very fun and super practical look at Cosmos DB's best practices through the story of, get excited, Spacey Sprockets.
Jane, get me off this crazy thing, right?
Yeah.
Well, at least if you don't have a well-architected partition key, right? Always on availability, low latency across the galaxy, and keeping costs under control. Those are all trade-offs we all face when we build real systems. But you know what? we're going to talk way more about that. And I want to just make sure that we're acknowledging you, the audience. So let's take a quick look. We've got some really, really nice comments, but I wanted to just show this one, the thought processes people go through when designing solutions. There's a lot. You have to make so many considerations when you're designing a production application. And you know what? You all are here to learn about that. Patty, what do you got?
Yeah, honestly, for me, I've got nothing but love in this group chat or in the comment section. So please, if you are around, we love to hear from you. Feel free to drop a comment, share what you're building, or just show some love.
Yes.
But we're back into the program.
Thank you for the love.
Oh, thank you.
Thank you for the love.
We're shifting into one of the most important patterns in Azure Cosmos DB.
In our next session, one of my favorite teammates, I know yours too, Justine Kochi, takes us deep into the Azure Cosmos DB change feed, how it works under the hood, the patterns that hold up at scale, and the live demo of debugging and lag. Recovering processing in production is going to be great.
Yeah, you know, Jay, Justine is amazing. And if you love Justine,
yeah.
And if you haven't used change feed, every write becomes a durable ordered event stream that you can fan out to services, search, and analytics. Event-driven architecture without staying on a message bus. So let's hear it all from Justine. Here's mastering the Azure Cosmos DB change feed, patterns, scaling, and real-world architectures.
We'll see you soon.
Hi, I'm Justine Kochi, and I'm a program manager on the Azure Cosmos DB team. I'm really excited to talk to you about change feed today. We'll cover what it is, how to read it, and some tips for debugging for real-world applications. So first, what is the change feed? It's a persistent record of all changes to items in your container that's ordered by modification time. As your client app is making writes to your items, you can then read them in the change feed with your consumer app. Your change feed consumers are processing changes per partition. So let's take a look at what that looks like under the hood. Because Cosmos DB is a distributed database, your data is distributed across multiple physical partitions in a container. In this example, I've got 3 physical partitions. Each physical partition can have its own independent change feed reader that's reading the changes in order for that partition. Order is guaranteed within a logical partition key in your physical partition range. Your continuation token tracks progress of that change feed processing for a given container. And this means that each of your partitions can have independent continuation tokens and independent processing. This is great for efficiency because it really allows you to scale your change feed processing even for extremely large containers with a high volume of writes. There's a couple of different change feed modes that you can choose from. The default change feed mode and what's enabled on all of your accounts is latest version mode. In this mode, you get the latest create or replace for every item. Items that are deleted from your container no longer appear in the feed, and this means you won't get a notification for deleted items in the change feed itself. Any item that still exists in the container, you can read the latest version of it. There's infinite retention of all of these changes in your container, and you can go back and reading even from the very beginning of your container to get all of the items and their updates. This is really great for a lot of change feed scenarios and powers most change feed apps today. There's also all versions and deletes mode. With all versions and deletes, you get every create, update, and delete, including TTL expirations. Items for TTL expirations will appear in the feed in order of their purge time, which may be slightly later than their actual expire time. Retention of changes in this feed is based on the continuous backup window for your account, so either 7 days or 30 days, depending on what you've configured. You can read all of these changes within that window. This mode is really great for audit logs or real-time processing where you need to react to every change. Consider an application that is replace heavy, where you have a high volume of updates to a single item within a short period of time. For all versions in deletes mode, you would get every single update in the feed, whereas latest version, you would only get the latest version per change feed pull. Depending on the needs of your application, each mode may be a better fit. So it's important to consider what your app is trying to do and choose the mode appropriate for your application. There's a couple of different ways to actually consume the change feed, and we're going to cover 3 of these ways. The first is the change feed processor. This works on a monitored container, or the container that you're reading your changes from. When you create a change feed processor, you can create multiple instances to handle scaling of all the partitions. And this is the compute environment that you're actually deploying your change feed processor on. So you can imagine this like AKS, where you'd have multiple pods that represent multiple instances. The code that's actually being executed when a batch of changes is processed is your handler delegate. This is like the business logic or the brains of your change feed processor. Here is where you handle what you're reacting to for the change. Maybe it's writing to something downstream, or maybe you're doing some analytics. This is really where you write your change feed logic. And the change feed processor is available in both .NET and Java. Now, as your changes are being processed, the lease container helps to maintain state and checkpoints for keeping track of where you are in processing for all of your various partitions. Let's take a look at some lease management and really understand how our physical partitions map to leases, which map to the instances. We've already established as a distributed database, Cosmos DB can scale out to multiple physical partitions. And each physical partition owns a range of partition key values. That top row is our physical partitions. In this example, we have 6 physical partitions, and each of them have their own lease. Leases are always one-to-one with partitions, and this is managing the state of where we are processing in terms of the modifications to that individual partition. You'll notice they each have their own continuation token, which is what maintains the state. Now, your change feed processor is deployed across multiple instances, and each instance owns a number of leases. These are evenly distributed across instances to ensure that as you're processing, you can keep up with these changes. Assume you only had one instance that's handling all of your leases. If that instance goes down, it might impact the resiliency of your application. However, if you have more instances than the number of physical partitions, you would have idle instances that aren't able to do any work. The change feed processor automatically rebalances leases across these instances to ensure the maximum efficiency of your processor. Let's say one of your instances goes down, the leases that are owned by that instance will automatically be rebalanced across all of the other healthy options. The next way to read change feed is through the Cosmos DB trigger. This is an Azure Functions trigger that is a really simple way to read change feed. It's built on change feed processor under the hood. So all of the lease and distribution of partitions that we just reviewed still applies in the Azure Functions trigger. However, the management is done for you. Because it's built on Azure Functions, it's serverless. It has built-in auto-scaling to dynamically react to the number of instances you really should be having without over-provisioning instances that are not actively being used. This is a really easy way to build the change feed, and the logic of your Azure function is like the delegate in the change feed processor, where you're just responsible for the business logic of processing the changes themselves. The last option is the change feed pull model. This model gives you the most control over how to read the change feed, but also means you need to have all the safeguards put in place yourself. So there's no lease container for maintaining state. You instead use continuation tokens, where you're responsible for storing and maintaining those continuation tokens. You're responsible for any error handling. There's no built-in retries. You need to handle all of that in your client code. So while it does give you full control, it's also more code to manage. One additional benefit of the pull model, say you wanted to only process changes for a specific partition range. This is possible in the pull model because, again, you have full control over what is actually being pulled. All right, now that we've got our change feed app, let's talk a little bit about monitoring and how we can debug some common failure modes to ensure that our change feed app is resilient. Some of the key metrics to monitor for change feed are the estimated lag. This measures the gap between the latest change that actually occurred in your container and the last processed item in your change feed. This is going to be your most important metric for monitoring your change feed health. While this estimated lag gives you a number of outstanding changes, it is intended to be an estimate, and it's not always the exact number of changes that are actually pending. The key thing to measure here is not exactly what the number is, but the slope of how the number changes over time. Is your lag steadily increasing? Is it decreasing? Are you staying constant? This will really help you understand if your change feed app is healthy. Some other things you can take a look at is the throughput of your change feed processing. You can look at the number of items that are processed per second and the RU consumption of your change feed processor. It's important to look at RUs not only of your source container that you're monitoring the change feed of, but also the lease container. If you have a lot of lease rebalancing and redistribution, that can put strain on your lease container, which typically is provisioned with a relatively low number of RUs. Monitoring these things will ensure that your change feed application is healthy. Digging deeper into the leases, you can look at the owner distribution. Are your leases evenly distributed across instances? Is the last checkpoint increasing for each of them, or is one of your leases stalled with processing? For setting up the monitoring itself, you can use Application Insights or OpenTelemetry, which is built directly into the SDK to make it really easy for you to export this telemetry for your change feed handlers. For alerting, some things that you might consider creating alerts for is sustained lag growth, or if there's any partitions that have stalled and are no longer making progress in processing. We can look at a couple key failure modes and some resilience patterns to help combat these. The first is, as changes arrive, they're processed in batches. When everything is going smoothly in the happy path, your process handler succeeds and your lease checkpoints are all updated. However, because these changes are processed in a batch, what if there's an error? Unhandled exceptions can create issues in your processing. While the change feed processor does have retry, you don't want to infinitely retry these poison messages that are not able to be handled after multiple attempts, and instead consider writing them to something like a dead letter queue. This will allow you to write the item that is failing to take a look at it later instead of blocking the entire processing for that container, for that partition, because your partition would not be able to continue making progress if you're getting a consistent error. There may be other causes of silent stalls for a given partition, and one of the common causes is outgoing calls. So if you're making calls to an outgoing service and they're failing, this can also cause errors in your processor that will stall your change feed. You can implement the circuit breaker pattern to ensure that you don't flood this downstream service and inhibit your ability to actually recover from these errors. A lot of the key resilience patterns for any application also apply to change feed, and it's important to keep these in mind for the most resilient application and processing. Now, we also talked a little bit about RU throttling. For consistent RU throttling, you can consider implementing priority-based execution to ensure that your mainline transactions on your container, maybe your writes and your reads, perhaps they have a higher priority than your change feed processor. With priority-based execution, you can specify that in the client to ensure that the change feed is not accidentally consuming extra RUs that you'd maybe prefer go to the rest of your application. There's also throughput buckets that will help you indicate the percentage of RUs that you want to distribute across your various applications and including your change feed. Now, while you may see RU throttles across your entire container, it's also important to consider hot partitions. Because the change feed works at the partition level and your progress is per partition, if you have a surge of writes that is generating a hot partition, it may be difficult for your change feed to keep up. Ensure that your leases are appropriately balanced across partitions, across instances, so that if there is a hot partition, it doesn't overload one of your instances and result in a higher lag across the board. All right, let's take a look at a demo to see how the change feed processor is actually configured and see it in a real application. I'm going to pull up VS Code with a simple app here. I've got a social media app simulator, which is really just two console apps. My first console app is simulating users creating, editing, and deleting some of their posts. And the program that we've got on screen here is a second console app that has our change feed processor. Now, because we know that we've got updates and deletes, and I want to react to all of them, I'm going to use the change feed processor with all versions and deletes mode. When I configure my change feed processor, I can choose a processor name. This tells me the unique processor instance and will allow me to coordinate multiple compute instances all to the same processor application. This is really critical for least rebalancing because if you're using different processor names, the change feed will assume that it's for actual different change feed instances and different purposes. So we've got the processor name, which sort of ties all of our instances together. And we also have our instance name. We'll take a look in the console app how the instance name allows us to tie multiple different processes of these together into that same processor. I'm using the same lease container for all of these, which is storing all those checkpoints. And I'm also setting up a couple of notifications. These lifecycle notifications are really important for debugging the lease ownership in your application. And you can get notifications for lease acquired and lease released, as well as printing out some error messages that may occur. So this is the change feed processor itself, but let's also take a look at the delegate. Once we get a batch of changes, this is the code that will execute and actually process those changes. So first, we'll simulate some extra processing with a short delay. And of course, in your real application, this is whatever business logic you may have. Then we can process our changes slightly differently depending on the operation type. The first thing we want to check for is any deletes. The ID and partition key of deleted items will come through in the metadata, so we can pull out those key pieces of information to be used later. For creates and replace operations, we can directly get the ID and the user ID, which is our partition key, from the current aspect of this change. Scrolling down a little bit further, this change feed is writing to a notifications container, which then can power notifications for our social media app. So now that we looked at the code, let's see it running in action. And I've got 3 separate terminals pulled up here. The first thing I'm going to do is start running my social simulator. So this console app is going to be creating items and posts from users in our application. Then I'm going to run my notification processor. Now, notice I'm not submitting any arguments here. It's just that basic code that we talked about, and it will have a default instance name, which we'll see spin up here in just a second as the detailed stats come online. Now, in the meantime, I'm going to start a stream of posts in my application. And let's make sure our processor is printing in verbose mode so we can see all those creates coming in. But we're using all versions and deletes, so let's simulate some delete events and some edit events. And you can see all of those are actually flowing through into our processor instance. All right, let's turn it back into quiet mode so we don't have every single change, but just the batches of changes that are coming in. And let's simulate a couple of viral bursts. There's a lot of buzz on our social app, and users are making more posts than ever. As we see these viral bursts start to flow through, we see the lag is steadily increasing on our change feed processor instance. So we can create a second instance to help us manage all of the changes that are coming through for all of these partitions and balance it a little bit better across both of these. So I'm going to print out the detailed stats for our second instance. And you notice that this one is named instance 2. As it starts up, we start by acquiring a lease, and we get an error on our initial processor. Now, this is really important because this is not actually a bad error. This error is just telling us, hey, I lost a lease and it went to someone else. This is the behavior that we actually want. Change feed processor is automatically rebalancing leases for us so that we can ensure they're evenly distributed across our processors. If we print out the leases that are actually owned by each of these, we can see our first instance owns 3 of our leases and our second instance owns 2. This is great because this means that our processors are working properly and our load is evenly distributed. Now I'm going to go ahead and shut back down our second instance, and we should see these leases redistribute back onto our initial processor. We see those lease acquired messages now. And when we print the leases owned this time, we see all 5 leases are back onto our main processor. Let's go ahead and shut down this application, and we see how easily change feed allows us to spin up new instances, and dynamically react to the volume of processes and changes coming into our container. All right, flipping back into slides, now that we've shown a basic change feed app, let's take a look at some advanced patterns. We can combine the event sourcing, CQRS, and materialized views pattern to create a really powerful application in Cosmos DB. While our demo showed creates, updates, and deletes inline to items, with the event sourcing pattern, every write, every create, edit, delete actually becomes its own independent create event. So it's a depend-only event store. We can write these commands into our event store, still stored in Cosmos DB as a container, and we can use change feed to read this ordered log and populate some downstream systems. These are also known as materialized views, and it helps us craft a view of our data that is better suited for the read patterns of my application. In my app, I've got a couple of read patterns that I want to support, like show me my notifications. This is that notifications container that we were just populating in our example. But let's say we also want to get posts by topic, or maybe we want to create a search index container. We can use built-in full text search with Cosmos DB to create a second container that has full text policies on our content. And this allows our users to really easily search across those data patterns too. So with materialized views pattern, setting up all of these separate containers based on the read pattern that we're trying to optimize really gives us the best configuration for Cosmos to give us these efficient reads without impacting our write path. Our write path is still optimized for the writes. Now, the materialized views pattern is really common in many databases, but I do want to highlight a Cosmos DB feature that makes this pattern really easy. We have a feature called global secondary indexes, which are effectively managed materialized views directly into Cosmos DB. So while I just showed you how you can kind of build this yourself with the change feed, reading the change feed of social events, populating a new container with a new partition key, you can add a global secondary index. This will do the exact same thing for you, but it will automatically maintain the secondary container without you having to write the code to build and manage change feed yourself. This is a really powerful feature that allows you to build containers specialized to the read patterns that you have. My container, I had 5 physical partitions in my source. If I were to use my source container to serve this query by topic, it would be really inefficient. It would be slow because I'm checking every physical partition. And it also would cost a lot of RUs. With GSI, I'm able to automatically create this, and I don't have to manage the change feed myself. So let's take a look at the Azure portal, and we can see how this is actually implemented. I have my change feed application, my Cosmos DB here that was powering that change feed app we just looked at. And you can see my source container is social events. Now, my source container is partitioned on user ID, and we see all of the posts that my users are making here. But I added a GSI already. So let's take a look at our GSI. And we can see this has a persistent copy of all of the items in our source container, but now it's partitioned by topic. And this is automatically maintained by the change feed. So we ensure any writes only go to social events. We don't need to handle any dual write or error handling. That's all given to us by the platform. And we're able to have this read optimized view. Now let's take a look at a query. So I want to get the top 100 items where the topic is Cosmos Conf. And this first query is against my social events container. And if I look at my query stats, I can see this costs almost 27 RUs. So that's quite a bit of RUs to get these topics. But if I issue that exact same query against my global secondary index, flip over to query stats, I see this costs just about 5.5 RUs. So this gives us an roughly 80% savings, all because we're using the GSI, which is partitioned and configured for our read pattern. This demo really shows us how you can use change feed and manage features to give you the best configuration for your specific applications. All right, we covered a lot today. So the key takeaways are that change feed really powers a lot of event-driven applications. There's many architecture patterns that help you build these apps for your business use case. When you're using the change feed, consider the change feed mode that is best suited for your application, and also the consumption model, whether that's change feed processor, Azure Functions, or the pull model. It's important to invest in monitoring, and you can use the estimated lag to ensure that your processors are keeping up. Keep resiliency best practices in mind in your handlers. Ensure that they're idempotent as retries are happening, and their resiliency is all the best practices with circuit breaker, retry, timeouts, etc. Advanced features like global secondary index really help you simplify these patterns and let the platform do the heavy lifting instead of you needing to manage that change feed application yourself. Now, you can get started and learn even more about change feed at this link, aka.ms/AzureCosmosDB/changefeed. Thank you so much, and I hope you enjoy the rest of the conference.
Okay, hello everybody. So this is Multi-Cloud DB, write once, run anywhere. I'm Theo Van Cry. I'm a PM in the Cosmos DB team. I work on SDKs, connectors, developer experience, and lots of fun stuff like that. But I'm going to be doing something very different this time, probably the first time we've done anything like this on Cosmos DB Conf. I'm going to be talking about something that we're calling Multi-Cloud DB. This is a unified data access layer for best-of-breed cloud databases. So for the first time ever, we're talking about databases other than Cosmos DB. But before I go into that, before I talk about what that does, I want to set some context here. So why teams still want cloud-native databases? Of course, databases like Azure Cosmos DB, Amazon DynamoDB, Google Spanner are still very highly sought after. They offer high availability and elasticity built from the ground up in those platforms. These platforms are built to exploit cloud core properties in those environments. They have strong operational guarantees and SLAs and managed scaling. It's simply not possible to get this same kind of performance if you're installing a traditional database software and putting that onto VMs for obvious reasons. And of course, you have a fast path to production without owning the database or the control plane. So everything is very easy, it's very elastic, it's very scalable, it's very, very highly available. And so the benefits there are pretty obvious. But teams tend to want managed database upside without the irreversible coupling that you tend to get. So there's a tension here. The deeper that you adopt native SDKs of these types of databases and query models, the harder it becomes to move anywhere else. So this becomes something that is concerning for customers if they want to exit the architecture or move into another cloud. And portability concerns show up pretty much before any line of code is written. And so sadly for us working on Cosmos DB and for our counterparts in Amazon and Google, often these very good database services get excluded right off the bat because there's no portability. They only run in Azure or Amazon or Google, etc. And so the cloud native benefits are obviously significant. Everybody knows that. But so is architecture level lock-in and risk. And this is very real. And we are obviously recognizing this. So the customer reality is that customers do want the benefits of cloud native databases, as we've said, but they also need a story for portability, procurement, and regional strategy, and so on. This is the gap that we're trying to fill with multi-cloud DB, and it's designed to close. So portability is no longer optional for teams who are building these types of applications, operating across regions, customers, and different clouds, and so on. And we see two different types of multi-cloud portability pressure, if we can put it that way. The one is cross-cloud deployment. So this is where you have the same solution delivered into multiple clouds, typically white-labeled products, sovereign deployments, or maybe partner-managed environments, where the application needs to behave consistently, even when the backing database changes by the customer or region, etc. And then the other one maybe is more familiar, is where you want to deploy into one cloud, but you want a credible exit strategy. In other words, you want to avoid cloud vendor lock-in at least, and portability obviously matters there. as well, even if the team never actually switches cloud providers. And so in both cases, the requirement is the same. Application code doesn't want to have to be rewritten if you're moving into a different cloud. And again, sadly for us working Cosmos DB, this means a great database product is often excluded right out of the bat because it only runs in Azure. So there are some abstractions out there. In the Java world, you have things like Spring Data and Hibernate, of course. In the .NET world, you have Entity Framework Core. In Python, you have things like Django, etc. That offer something close to this. So you'll get something like a programming to an interface model. In Spring Data, you have repository abstractions and object mapping and so on. And you get something like a productive lowest common denominator. The problem with this is that they're not based strictly on portability contracts. This is a side effect of developing an abstraction that is meant to simplify development on many different databases, rather than it being the core design goal. So what you get over time is a divergence still appearing. You still get query features drifting by backend, annotations and mappings, code level changes that you need to apply, even though more or less things tend to be very similar. So portability is sort of possible in part, but it's not guaranteed by design. And in practice, this shows up when you want to migrate from one cloud to another. You still have, in some cases, almost as many changes, if not quite as many, and divergence still accumulates because, as I said, this is not the core design goal. It's a side effect of some principles to create an abstraction that you get some level of portability, but it's not really completely portable in that sense. So why multi-cloud DB? And what we've built here and what we are building is different. We have a strict portability design goal from the ground up. This is not a side effect. Capabilities explicitly surface what is and what is not portable. The promise that we're making is write once, run anywhere semantics. Multi-cloud DB treats portability as a product guarantee, not a best effort convenience that you get as a side effect of some goals of abstraction and whatnot. So again, design goal, strict portability, same CRUD and query code should run unchanged across Cosmos DB, DynamoDB, and Google Spanner. It should be portable by default, transparent limits. We will be providing some native escape hatches, but we don't expect customers to be using this. The whole point of this abstraction is that you shouldn't be using those because that will obviously break portability, and that's what you want if you're in this space. So simple architecture view here. You have a Java application that's going to be connecting to multi-cloud DB client, and then you have a service loader discovery that's going to load the appropriate module that is being driven by config files only. And this is very similar to what you get out of things like Spring and Hibernate and so on. But again, as we've said, this is portability from the ground up and strict guarantees around not only the feature set, but the behavior of those features as well. And it follows from that, we need a portable query DSL. So you can see on the left there, this is multi-cloud DB query DSL, the same regardless of the platform that's running on. It would be different on the right-hand side, syntax differences between those different databases and so on. It also follows that we have a fairly conservative feature roadmap. Bottom line is, example, a feature will not be supported if all providers cannot support it. So if it can't be supported in every available provider, then it's simply not shipped. So you might be wondering at this point, why would we be crazy enough to do something like this? And the answer is, of course, we've done this before. Those of you who are familiar with Cosmos DB, Azure Cosmos DB was the first database platform to build broad compatibility APIs at this level. Those of you who've used MongoDB API, Cassandra API, Table API, Gremlin API, and so on. These were compatibility APIs sitting on top of Cosmos DB, providing the surface area of a different database on the same platform. So this gives us years of real-world experiences handling compatibility drift, behavior gaps, edge case semantics, etc. And we've learned that how portability fails in practice, where feature gaps create friction and so on, how to set clear contracts. and manage the relevant trade-offs, etc. Why this matters? Well, this is not our first rodeo, as my American colleagues would say. We're applying hard-earned compatibility discipline to multi-cloud DB from day one. And we actually think this is the easier problem of the two. Compatibility APIs are hard. Fitting a database engine to a programmability surface area that we don't control is difficult, let's say. Surface area keeps expanding, behavior contracts keep shifting, goalposts move continuously. It's very difficult. Now, I'm not going to say that multi-cloud DB is easy, but certainly from our perspective, given our experience, it's a more tractable problem. We can constrain the programmability layer that we control across a focused set of databases, and therefore we define the contract, the portability of the contract. We scope that to known database targets, and we can enforce limits explicitly. So we have more control, even though there are challenges, will be challenges around supportability. It's certainly a more tractable problem than the one that we have already solved in the past with Cosmos DB nonetheless. So, of course, where this fits best, of course, if your most important things that you want to solve, that you want the benefits of cloud native databases, the elasticity, the high availability guarantees, the SLAs, and so on, the managed service aspect, but you also want portability, then this is going to be a great fit for you. Of course, there are trade-offs to accept, as there are everywhere. Strict portability means some trade-offs. Of course, you are going to get access to more granular features if you're using the native SDKs for Cosmos DB and DynamoDB and Google Spanner and so on. So bottom line, you want to be choosing this when portability and the benefits of a cloud native database are really the higher order bit for your architecture and for your strategy. So then again, ultimately, the key takeaways: managed cloud databases are still very, very attractive to many customers for some very good reasons. High availability, elasticity, performance, maintenance, operational guarantees, the list goes on. The blocker isn't really the database capability, far from it. It's, of course, the application level coupling to one provider's SDK. It's lock-in. We don't like to say the words lock-in, but that's really what we're talking about here. And multi-cloud DB is designed to blow that open by having a strict portability design from the ground up, so teams can keep an exit strategy and deploy in cross-cloud scenarios without giving up the massive benefits of modern managed cloud databases like Azure Cosmos DB and our counterparts in Amazon and Google and so on. So before I do a demo, I just want to mention we do have some documentation, and you'll see there, it says at the bottom there in small print, the SDK is currently available as a public preview. It is not yet fully ready for production use. Expect breaking changes, incomplete features, limited support during this phase, but we definitely will encourage you to try this out. Raise issues in GitHub, ask questions, make feature requests, etc. You want to know how you want to use this, what this is solving for you. We're definitely committed to it. So yeah, check out the documentation. There's a nice getting started guide, a developer guide as well. It's fully comprehensive with everything that we have so far. And obviously we're going to be developing on this. Information about compatibility, a couple of samples that you can get your teeth into, an API reference, and so on. All right, so without further ado, let me set up my demo here. Okay, so here we are in VS Code. I have an application called Risk Platform App. It's a multi-tenant app that is giving a dashboard of different applications that are providing risk management services and so on. And this is built on multi-cloud DB. And you can see the multi-cloud client is being used here. And that is going to do a bunch of things. And one of the things that it's going to do is load a config file. And again, I mentioned earlier, the configs are the only thing that are different per provider. So you've got one for Cosmos DB here, and one for DynamoDB, and everything else is identical. The code is the same regardless of which provider you're pointing to. You don't need to change it. You can treat it as basically the same database, and we guarantee that the behaviors and the functionality that is available to you should be the same, and performance differences within some acceptable limits of a statistical difference. So let me just start up my Cosmos DB version here with the Cosmos DB properties that I have. So let's go ahead and start this one up. Okay, so that's started up. So let me go into this app here. And we can see I've just put a little moniker there just based on the config file to denote which database it's pointing to, but everything else should be identical if we were going to run this in Amazon. And so you can see here I've got different portfolios. If I click on these, I'm going to see a different list of positions on those portfolios. So just to prove it, let me go back here and let me cancel this app. And let me start it up again, but use the DynamoDB properties files instead. Okay, so that's started up now. You can see there, the provider DynamoDB. Instead of just clicking on the link, I'm just going to go straight back to my original link here, and I should be able to refresh or hit that URL. And you see it's just now pointing to DynamoDB, but everything else is exactly the same. The data is the same, and all the behaviors should be identical. And if we were to look in the portal for Cosmos DB now, of course, this is where things may look different. So you'll have databases and containers in Cosmos DB. For those of you familiar with Cosmos DB, and in Dynamo, of course, you have tables, but you don't have databases. So we prefix this with the database name in order to replicate the resource hierarchy. And so that's from the SDK perspective, that's what it's abstracting. But of course, the data is ultimately identical. And most importantly, of course, how the SDK interacts with the data and the results that come back and the behaviors should be identical as well. And ultimately, that's what you will care about if you want to maintain a single playbook, a single set of application code for your solutions that are being deployed into different cloud environments, or if you want to make sure that you have an easy migration and exit strategy from one cloud environment to the other. So that's it. That's everything for multi-cloud DB. Again, check out the documentation and the links that we gave here earlier on. Thanks for watching.
Hey everybody, my name is Andrew Ruffin. I'm a senior product manager here at AMD, and I focus on launching and growing new products and services on Azure with AMD under the hood. You're here at Cosmos DB conference, most likely because you care about building systems that actually work at scale. They're globally distributed, they're highly available, and they're predictable under real workloads. Azure Cosmos DB gives you all of that as a managed service, and that abstraction is incredibly powerful. Especially as a managed service, this all comes by design. They come from real engineering decisions, joint enablement, and the deployment of actual infrastructure across the global scale that only Azure can provide. The hardware choice isn't your concern, but the physics absolutely stick around and they matter. And that's where AMD comes into the picture. Today, Azure Cosmos DB runs on modern AMD EPYC processors across the globe. We launched AMD EPYC in the cloud on Azure nearly 10 years ago, and we've continuously executed and generated new products and services that give the features that you need generation over generation. You'll hear more details on how Azure Cosmos DB takes advantage of AMD infrastructure, including the latest 5th gen processors later on. While you as an Azure Cosmos DB user don't need to spend any cycles worrying about the hardware or the infrastructure, you get the benefits in terms of cost savings enabled by efficient and sustainable performance. Across Azure, you'll find benefits when you're running on top of modern EPYC processors. The newest V7 generation, for example, provides up to 35% more performance and performance per dollar over the prior generation. With these newest generations integrated into Azure Cosmos DB, you get more performance per request unit and a better experience to the many dynamic scaling and elasticity features that the team continues to roll out and you hear more about later today. This is all enabled by the close partnership we at AMD have with Microsoft as a whole, and it creates a feedback loop between hardware and software development. This results in optimized performance per dollar per watt for the most advanced workloads, like the ones you run every day on Azure Cosmos DB. So thank you to the Azure Cosmos DB team and all the organizers of the conference. We appreciate the opportunity to help put this all together and make this possible. Enjoy the show.
Welcome back, and a quick thank you to Andrew Ruffin and our partners at AMD for being part of Azure Cosmos DB Conf.
Yeah, absolutely. They were a key part of how we were able to extend this show to 5 hours. More sessions, more speakers, and more depth. Quick reminder, you can explore the full agenda of all those talks at aka.ms/Azure Cosmos DB Conf all of the talks, all of them,
All of them.
they're going to be live. Tell them about it.
Yeah, there's going to be 21 sessions total, and every session will go live before the end of today's show. You can find all of today's links up in the YouTube description.
A lot of links. So yeah, you're going to be looking past the comments. So we're going to talk a little bit about agents, AI. But before we do that, we've got some comments from you that have to do with agents and AI. So let's take a look. One of our viewers, a very, very engaged viewer, Shanolo, has said, I asked the chat, and I'd love you to answer those questions too, what your AI agent development environment may look like. And they said we are using GitHub Copilot. At the enterprise level, we've developed our agents to run widely with Copilot CLI, using it for code, test, DevOps. That's huge. It's an end-to-end kind of experience. And then Sandru says, I am a DB admin who usually uses the Azure portal for DB management and bicep templates for deployment. So they do have a Copilot with PowerShell for doing that automation. So, hey, Patty, I hear you also got another question about something related to AI coding.
Yeah, also from St. Andrew. First of all, thank you so much for the great comment on the keynotes. Now, the question is about the agent skills. Does it only work with the extension? No. You can use it. You can use NPX to install it. Installation and usage instructions should be in. Should be in the documentation.
Yeah.
But what do we have, Jay?
Absolutely. And up next, when you're building with AI agents, token usage isn't just a billing detail. It's a design constraint. And so every extra turn and chunk of context adds up. So you need an approach that stays efficient as your agent scales. And I know I may get access to lots and lots of tokens, but not everyone else does.
I know. Efficiency really is key, and that's where memory becomes critical. Faral Abu will show you how an agent memory layer on Azure Cosmos DB helps you reuse context, reduce tokens, and keep response quality high while improving latency and keeping costs as predictable as you scale.
Yeah, absolutely. And I love this session. Farah is so great. This is cutting AI agent costs with Azure Cosmos DB, the agent memory fabric. Here's Farah.
Hello everyone, my name is Farah Abdu. I'm a lead machine learning engineer and AI researcher. And today I will walk you through how to cut AI agent costs with Azure Cosmos DB. This is a war story about building an AI system that costs way too much money and how I fixed it. So for the agenda today, we are going to talk about the problem, why the multi-agent AI pays money, the solution, we have one database, 3 features, then a live demo and the real production numbers. So, global AI spending in 2026 will be $2.5 trillion. The agent market grows from 7.84 billion to 52.62 billion. This is between 2025-2030, a compound of annual growth rate of 46.3%, and 75% of large enterprises will be running AI agents by 2026. And inference demand will grow about 1,000 times by 2027, and this will keep the cost low. Is not an optional thing. It's how we can stay in the business. So this is the architecture that everyone is building right now. 4 data systems, a cache, a relational database, a vector database, and an event bus. We have 4 pillars for this, 4 failure points. We have zero coordination between them. And this is exactly what I built first. It worked, but it didn't work after this. So what about the production? So in the demo, first of all, we have 3 agents. We have 100 requests. It's about $6. Then we come to production. In production, we have now 3 agents, still our agents, but now we have 10,000 requests. This will cost us $18,000 a month. Nothing changed about the design. We just got real traffic. So we have 5 failure modes I have seen with my own eyes. Number 1 is about the cost explosion. We have from $5 to $50 in a demo becomes $18,000 to $90,000 a month in deduction. Number 2 is the reliability collapse. So 95% per agent multiplied across 3 agents equals, for example, like 85.7%. This is 1,430 fillers every day at 10,000. Huge number. So number 3 is about the latency cascade. For example, agent 1, let's say, takes 3 seconds. Agent B take about 4 seconds. Agent C take about 5 seconds. There are 12 seconds total plus 200 to 500 millisecond coordination between the handoff. And for the state corruption, like parallel writes with no concurrency control, it means silent data loss. And 5 is the context degradation. Agent C gets only 60% of Agent A original intent after 47 steps. So what is the reliability math that kills you? One agent at 95%, 500 filler a day at 10,000 requests. 3 agents at 85.7%, 1,430 filler per day. We have 5 agents at 77%, 2,300 filler. I'm gonna say 40% or more of agent project will fail by 2027. So look at this math. I think it's huge numbers. The LLM pill now that nobody planned for. VentureBeat analyzed 100,000 production queries. 18% were exact duplicates. 47% were semantically similar. Same meaning, different words. Only 35% were genuinely new questions. When I run the same analysis on my own system, about 65% of my LLM spend was answering question I already answered. So the breaking point is $47,000 a month. 40% of the sprint time debugging agent fillers. Multi-agent debugging takes 3 to 5 times longer than the single agent debugging. And only 11% of the organizations have AI agents in production at all. We were in that 11%, but it didn't feel like success. Something now had to change. And this is why we are here today. We have one database, 3 capabilities. The agent memory fabric, which is built entirely on Azure Cosmos DB for NoSQL. This replaces 4 systems, cut the cost is 73%, cut the latency 65%, and let me show you now how. So why Azure Cosmos? Because we have 4 properties that make it uniquely suited for the multi-agent workload. First, the native vector search using the disk NN. Sub 20 milliseconds at 10 million vectors, under 100 milliseconds at 1 billion vector. The second is the change feed, like the built-in event streaming, no message queue needs. And the third is the ETAG, optimistic concurrency at the document level, no distributed log manager is here. And the global distribution, so multi-region, 99.999% SLA, single-digit multi-second point writes, all-in-one SDK, one string connection, all in one pill. Now, we know that a traditional cache matched exact strings, 18% hit rate. A semantic cache matched meaning using the vector similarity, 65% hit rate. The extra 47% is the money you are leaving on the table every day. The query on the screen does it in one SQL call, vector distance with a threshold of 0.80. If the incoming question scores at or above that, returns a cache answer, no LLM call. Now for the embedding pipeline. We have 4 components: an embedding model, which will be a text embedding 3 small by the Azure OpenAI, 1536 dimensions. Then we have a Cosmos DB container with a distinct and vector index, TTL per item from 30 seconds to 7 days, partition key, which will be the query hash. And we have the vector index configuration, which where we set the indexing search list size between 10 and 500 to tune the accuracy versus build the speed. And then the lookup query, which will be the select top one with the vector distance greater than or equal to 0.80. Below that, call the LLM and store the new entry. So now let's have a look how this works live. So we have here, this is the entire cache lookup. One SQL query, we have the vector distance built into the Cosmos DB, no extra library, no separate vector database. Then I have some agents to try on. This is the first one with 3 questions, and then we have a next run with another 3 questions to see the cache hit and the cache miss. So if I run the demo, we have here 3 pilots on the screen: semantic cache, change feed, optimistic concurrency, all in one database. The first agent, as you can see here, like, for example, it have a support agent with what is the refund policy for electronics. It have a cache miss. It doesn't find this before. So now we have the answer. The second agent, the return agent. How can I return an electronic product? The third agent about the product itself, a warranty on laptops. So now we have mess, right? Now what if I just change the question again? So I will just comment this, uncomment the second one, or the second run. It has similar questions, similar meanings, but not exact same writing. So here, for example, what is the electronics return and refund policy? Then electronics item I put, then the warranty comes with the laptop. So let's run this one more time. So as you can see, we have here a cache hit, similarity 0.89, which is more than the 0.80 we have gotten in the slide. The second one is also a cache hit, similarity 0.91. The third is also a cache hit with 0.92. So it finds all of these info on the database. It doesn't need to call the LLM again and cost me money. So how much it saved you? It saved me now just $327. Okay, let's go back to our slides. So what you just saw was 3 agents, 3 different questions, 0 LM calls, all answers compact in about 1 second. I say what is electronics return and refund policy, and I found it matched the refund policy for electronics, for example, at 0.89 similarity. A traditional cache would have missed. A semantic cache catches it every time. So the production results, and this is the results from a real production deployment, which is consistent with the VentureBeat's published benchmarks. Before, $47,000 a month, 850 millisecond average latency with 10% cache hit rate. After that, I have $12,700 a month, these 100 millisecond average 300 millisecond average latency and 65% cache hit rate, and 73% cost reduction, 65% latency improvement. One architecture changed it all. So what about the disk and at scale? Let's say, so under 20 milliseconds at 10 million vector with greater than 90% recall, we have under 100 milliseconds at 1 billion vectors. This is still greater than 90% recall. 70 IU per query, less than a complex SQL query. And when the index grows 100 times, the latency increases less than 2 times. And for the change feed, we have two ways, the traditional way and the agent memory fabric way. The traditional is where the agent A will be sent some message queue, and the queue delivers to agent B, 200 to 500 millisecond end-to-end handoff, plus the cost of the queue service. With the agent memory fabric that we have just had, the agent A will write to Cosmos DB, change feed triggers agent B in real time, and no queue to deploy, monitor, or to pay for. So the database is the message bus here. The three patterns I use in production are, first of all, the fan-out coordination. So one agent will write, many react simultaneously, and partition by the task ID. The pattern 2 is that state machine translation, where the status moves pending to planning, to execution, to validating, to complete. So we have all the status in front of us. Change feed fires on every transition. You get a full audit trail for free. Pattern 3 is competing the consumers. Multiple agent instances share work from one partition. The least procedure will rebalances automatically when you scale from 1 to 100 instances. The problem was that agent A and B both read the same document, both write back, last write win, and the first write is silently lost. That's why I have here the mistake concurrency. So we can prevent the corruption. And the solution is the e-tag, where every document have a version stamp. If a document change between your read and your write, Cosmos DB will reject the write. No distributed lock manager needed. Just a 3-line retry loop. What about the conflict resolution? So a 409 conflict is not an error. It's an information, and it has 3 patterns. First one, the last writer wins. Discard your changes, reread, retry, use when refresh data is here is always more correct. Next is the merge and retry. So fetch the fresh state, merge both changes, Retry with the new E tag used when the agents update different fields of the same documents. The pattern 3 is about partition and avoid. So design the partition keys so agents never write at the same document. The best conflict resolution is no conflicts at all. So here's the full architecture. We have like 4 systems, 4 pills, 4 filler points, 0 coordination. After that, we have 1 database, 1 pill, 1 SDK, 1 dashboard, same capabilities, and only 1 pill. So the lessons that I learned the hard way are listed here. These are the 4 things I got wrong. First one is the partition key. The partition key design done last, not first. It caused a painful live migration. The right key was /task ID, even distributed, plus the change feed locality, design it first. Number 2 is that I killed the vector index after loading the data. That causes a 90-minute window of 100% cache misses. Build the index before loading the data. Number 3 is the compliance team asked for an audit trail. Change the feed was already captured every state transition for free. It saves reproduction incidents through the replay. And number 4 is that start with the partition and avoid, not the merge and retry. The best conflict resolution is no conflict. So, for you now, what to build Monday morning? 4 steps. Create a Cosmos DB serverless account, 5 minutes. Then you'll create a container with a disk in and vector index on /embedding. 2 minutes. You need then to store the LLM responses with embeddings. That is my existing code with plus, let's say, 10 other lines. And before every LLM call, run the vector distance query first. You can have semantic caching in production by the end of the Monday. But why this pattern wins is because we can see that McKinsey Global Institute published a report in November 2025 says that AI-powered agents and robots could generate $2.9 trillion in US economic value per year. So the winners will not be the teams that build the most agents. There will be the teams that run them efficiently. This is what the agent memory fabric gives you. Thank you all. The code is open source. You will find this at this repo. I'll be around if you have any question. Please open an issue on the repo and let me know. Thank you.
Your favorite apps light up your world. Azure Cosmos DB powers the spark behind their shine with massively scalable data and built-in AI capabilities. Intelligence on the move. Audi uses Azure Cosmos DB to fuel AI assistants that deliver answers at highway speed. Creativity that connects. With Azure Cosmos DB, Adobe helps brands craft personalized experiences with real-time relevance. Color reimagined. Built on Azure Cosmos DB, Pantone's palette generator turns inspiration into expression. Goal! Premier League uses Azure Cosmos DB to keep fans close to the pitch with insights drawn from matchday moments. Talking cars? The future of in-car infotainment starts with TomTom and Azure Cosmos DB. Answers uninterrupted. Together, Azure Cosmos DB and ChatGPT, the world's #1 AI app, help 800 million users keep work moving with near zero downtime. From connected transportation to creative exploration and so much more, Azure Cosmos DB powers the AI apps that move the world forward.
Hey folks, welcome to a session about Azure Document DB. We have a really exciting session for you where I'm going to show you first what and how things work under the hood for Azure Document DB, what are the key functionalities, and how you can modernize your MongoDB compatible workloads that are on-prem or on the cloud with just a few clicks. So before we get into the slides and the content, let's go over a brief demo, and I'm going to show you how everything works behind the scenes. So over here, I have a website where you can where you place orders, and our website is called Contoso Retail. Think about it like a website like Walmart or 7-Eleven, where they have an online database where they sync up everything with their local instance, and every local store would have their own on-prem document DB server. So high level, to brief it up, we have a centralized database which connects all the local stores that are in person with all the local database for document DB for these stores that are available out there today. Over here, we have the global database. Let's also look at other databases that we have. So we have one store in Seattle, and then we have a second store in Chicago, and it's all connected to our global database, as I mentioned before. Now, let's go through our Seattle store and see what orders have been placed so far. So the last order that we had was a customer demo for like $249, and the status is still pending. You can even add your own orders right now. Let me briefly see how it works. We place an order, and the last order was just populated on the screen. And everything is going to be synced up to a global database, which is the Azure Document DB database. So if I hit refresh, the same order has been popped up over here with the same numbers and the same amount. But let's say for some reason your local databases are not working today. Your Wi-Fi is off there, or there's some kind of disaster that's happening. So we're going to try to replicate that in this demo as well. I'm going to click on Simulate Outage. So everything that's connected to your local database, to your online database, has been cut off. So there's no sync between the two. So if I go back to my Seattle database and add another order, let's add 4 items to the list and place an order. As you can see, we have an order created with order ID as last 4 digits as 5471. If I hit refresh, it's right here, 5471. But let me go back to my global database and see it has been synced up or not. Let's give it a few more seconds. Okay, now we are connected to a global database. Let me hit refresh. And as you can see, the last order ID is 5470. Now let's take a look at what goes on behind our database to make sure that we actually track this this order in our local database. So I have three sources over here. First is my Azure Document DB instance, which lives on Azure. Then I have a local Document DB instance, which is I've named as Chicago, and then we have Seattle. If I go to orders and documents and search for my last order, which was 5471, you can see it has popped up. It has all the items that I just placed an order for. They are titled by SKU names. It's still here. But if I do the same thing with my Azure database collection, and if I go to JSON view and search for 5471, nothing shows up. Like we don't have anything in our global database just yet. So I'm gonna cancel the outage and click to restore. And the disaster mode is off and the connection has been restored. And it knows all the changes that are in the pipeline are gonna be flushed to our global database. As you see, it just mentioned auto-synced one new order from Seattle store to global. It's gonna take a few minutes for it to pop up on the recent orders and we can take a look. The reason this is really crucial for you is because Walmart as a store and any store that are out there, you have like local stores that are running on a 24/7 basis. You cannot just rely on the cloud at every second. Everything, like, we know some things could go wrong. Customers, if they want to buy something, we cannot be like, hey, the internet is down, we cannot process your transaction. So that's why having a local database is really important for these stores. So as you can see, it just flushed one new change to the global database. Let me hit refresh again, and you can see the order ID 5471 has been popped up on our global database. And the amount, everything is like searched and filled up over here. So this is really crucial. Since we are a truly open source database, you can run DocumentDB on your local laptop, computer, wherever, or even you can run it on AWS, GCP, or Azure. It makes it so flexible for you to just manage your workload based on what your needs are. You're not tied into like one vendor or one service at a time. Also, I want to show you that there is a bidirectional sync between global and from local to global, as well as global to local. So let's say in this scenario, the Contoso retail store, they want to sync up everything like once a day, everything that's happened in like 24 hours of a local store to the headquarter database, so they can do like analytics, do reviews, and create like dashboards on how many orders were placed. We allow that as well. Let's say like global database makes an update to the product SKU, or a product pricing has been changed. Let's say the wireless headphone price goes from $249 to like $200. They're running a sale for Thanksgiving or something like that. So we can pull our data from a global database, and it's going to sync everything up with the local database that we have out there. And right now, we only have 3 databases stored. We have one Chicago location, Seattle location, and a global database. But you can have multiple stores and have like a bi-directional sync between all these stores. And if something goes wrong in one of the local stores, don't worry, your changes are not going to be gone forever. They're just going to be queued up, and they're going to be stored using change streams later once the connection has been restored and the disaster recovery has been fully committed. And you can also track what's going on for all these stores in our Azure service at the same time as well. So now let's take a look at how our data is being laid out behind the scenes using our own VS Code extension, DocumentDB for VS Code extension. So let's go and take a look at how our data is laid out for our online database, which is the Azure DocumentDB database, our local instances of DocumentDB, which is the Chicago store and the Seattle store. Let's go through our orders, and you can see we have all the information necessary needed for our online headquarter database. So if I click on the view for a specific document or a specific data point, you can see it has all the information necessary that an audience, that a headquarter person would need. Like, where was the data synced from? It said it was synced from the Seattle store at time April 16th at 7:30 p.m. It also has all the information of what the status of that information is. What was the total amount that was collected, and what was the items that were added to their SKU. Now, let's go and take a look at the performance for our online database. And we want to make sure that the performance is optimal, because let's say we have an online store like a Walmart, where people want to search up what products they're looking for. And if it takes forever for them to load the website, load the product they're looking for, it's just going to be a bad user experience. So now let's take a look at the orders and see how long it takes to find a certain item that we were looking for. So you can see we have multiple fields over here. One of the fields is status. So let's try to filter out based on the status of an order. So if I just do status and shipped and hit run, it's going to give me all the data points, all the documents that has status equals shipped. Now I want to take a look at the query performance for this exact same query. As you can see, it took like 3.5 milliseconds to examine over 15,000 documents to return only 2,866 documents. The ratio for examine to return ratio is 5:1, which is not good, because you don't want your database to do a full collection when retrieving information for what they're looking for. in this case, it's only 15,000 documents, but like a store because Walmart, there are going to be like millions and millions of like documents or orders in the database. And if we scale it up to those level, it's just going to be forever for them to get the information they're looking for. So that's why we built something which is very useful using AI, which is an AI-powered performance insights. Well, how it works is it already has all the information about your cluster, your database, how your indexes are stored, how your data is laid out, and the performance of your database. So it takes all that information, and we have a bunch of like skills that MD built right into it, which gives you the recommendation of what we think is going to be optimal for you. And before we even give you the recommendation, it tells you what exactly is wrong with your query. Over here, you can see the performance summary said, the query performance is poor because you basically did a full collection scan, and which is inefficient for filtering on the status field that we are looking for. You don't want to do a full collection scan when you're working with your database. So, and then it's going to give you a one-click recommendation solution where all it says is, hey, just create an index on the status field. And it gives us, we have the button for it, just click on create index, and it's just going to create the index for you. So as you can see, it took like 2 seconds, but the index has been created on status field we are looking for. So let me click over here, go to indexes, and just hit refresh. So we can see our status index has been created. So now let's run the exact same query to see the performance difference with and without an index. Voila, it's 1.74 milliseconds. So we actually reduced it by almost exactly half that time. We only examined 2,866 documents to return 2,866 documents that we were looking for. So this is how an index was actually optimize your performance. And that's why, so you don't have to read any like documentation or find the best indexing policies. That's why we brought everything together using AI to make sure your database performance is the most optimal you're looking for. And not just this only works on an Azure Document DB service. It works on any local Document DB service or any Mongo compatible database that's running out there. So let's do the same thing over here, and I'm going to open up a Seattle store and filter out by status equals shipped and run a find query. And it's going to give us, since we don't have an index on the status field, which is going to examine all the documents that we have to give us the response that you're looking for. So AI performance also works on a local instance as well as an Azure Document DB instance. Now, since we looked at the demo, everything worked well. Now let me give you a brief overview of what Azure Document DB is, or what is Document DB, and why we even built it in the first place. So you must be already familiar with MongoDB databases. It's the most popular non-relational database that is out there. It allows to specify documents in a JSON format. And JSON fits naturally into many web developers' code bases with the popularity of JavaScript. And it is very popular to build solutions like web and mobile apps, AI and RAG applications, and product catalog and personalization. So what is Document DB? It is an open source MongoDB compatible database built for flexibility, scale, and AI. It is now part of the Linux Foundation, and it has like industry support from Azure, AWS, GCP, Snowflake, Cockroach Labs, and so many more. It also gives us the ability to run your Document DB instance on AWS, GCP, and Azure at the same time, where you can like replicate information across all the clouds, so you're not like vendor lock-in. And also you can run it on-prem, like as I showed in the demo like a few seconds ago. So the mission of Document DB is it's built on principles of transparency, freedom, and standardization. Visibility. We want to ensure developers have full visibility in the underlying architecture. That's why with the MIT license, users have complete freedom to use the project as they please with no restrictions. It is an open standard. The goal is to create an open standard for Document DB databases for a universally accepted implementation standard. All right, so based on Document DB's popularity, we thought about let's also build an Azure first service built on this open source document DB, and we call it Azure Document DB with MongoDB compatibility. It is built innovative. You can build innovative apps with truly open source 99.03 MongoDB compatible document database in any environment. You can also deploy in Azure for the best enterprise experience with hybrid and multi-cloud capabilities. It has AI built right into it. It is a built-in no-cost vector search powered by scalable disk-NN. So you can combine your vector search queries and your full-text queries with hybrid search right into the database. So think about one database for all kinds of your search workloads. You don't need to ETL your database out of an operational database to a vector database like Pinecone or Vivid, something like that. Everything lives under one database, so you can run all your queries together. It is enterprise ready. We have authentication with Intra ID. You get all the perks of being an Azure service. We also give you up to 99.9995 availability SLA across the full service stack. It also is cost effective. It reduces the total cost of ownership by scaling compute and storage independently. And also 35 days of free backup and 24/7 support included in the price. So there is no extra cost for licensing or support or even backup. The price you see on the website is the price you pay every month. It is also only based on your compute and the storage that is required for your workload. There are a lot of customers that are actually using Azure Document DB today. We have AB InBev, UBS, KPMG, United Healthcare, a lot of customers for different workloads. Some of them, like EY and KPMG, are using Document DB for their vector search workloads for the AI native applications. And one of the key differentiator for Azure Document DB is its hybrid and multi-cloud freedom. Like the demo I showed before, you can run Document DB on any service that is out there, local, AWS, GCP, and Azure at the same time. And there is about unidirectional replication between all these services because it runs on the same engine that powers them all. And also, with Azure Document DB, you can lower your monthly cost by up to like 45%. And also we give like reserve instances. So if you commit for a year, we give up to 40% discount. And if you commit for 3 years, we give up to like 60% discount on your MongoDB compatible database. So you can save up to 50% by switching to Azure Document DB. And it gives you the best perks that are out there. We give up to like 32 terabytes per shard, free point-in-time backup and restore, and no additional support contracts or licensing. I'm going to emphasize this again. The price you see on the website is the price you pay at the end. There are no surprises, no additional contracts, licensing, or any other fees that are associated with Azure Document DB. But wait, there's more, and there's more discounts. We also give up to additional 20% customer incentive and discounts on top of 1% and 3% RI. If you're interested, feel free to reach out to us at documentdb@microsoft.com. And today we are introducing Premium SSD v2. With Premium SSD v2, it gives you the maximum IOPS and throughput for every disk selected at no additional fees. So you can do 80,000 IOPS and around 1,200 milliseconds per disk selected. So you can upgrade your speed, but it's the same price that you pay today. And we also have the LLM-based index advisor for Document DB, which I demoed like a few seconds ago. So it makes sure you get the best optimal performance from your database wherever you're running it from. And say goodbye to like manual troubleshooting with just one-click AI optimization. Then we also bringing advanced full text search capabilities in Azure Document DB. Think about Elasticsearch workloads that people usually run with their database. We are bringing all those functionalities built right in directly into Azure Document DB. So no more paying for third-party services for your search workloads. Everything is built right into your database. And some of the functionalities we're bringing in the next month or so is going to be fuzzy search, proximity search, multi-language support like Chinese and Thai, PM25 ranking, and rank fusion. So with rank fusion, you can run your hybrid search workloads with just one query. So you combine your semantic search and your full text search and use rank fusion to find the best optimal solution, best optimal documents in the database for your exact query. And in the future, we're going to bring on multi-field indexing, analyzers, and tokenizers, and like tokenizers filters, and so on. And did I mention we have the best-in-class vector search? We have performed significantly better than any other MongoDB compatible database out there There are so many benchmarks that have been reported about the performance with latency, lower latency, and like higher RPS. We also have a Microsoft AI built-in vector indexing, which is the disk-gain technology, which supports richer vector search capabilities. So you get high accuracy and speed. You can scale up to millions of vectors embedding with high accuracy and fast speed. We support up to 16,000 dimensions. For context, the largest embedding model that is out there is 4,096 dimensions, but we support up to 16,000. So let's say in the future, OpenAI, Anthropic, or Gemini comes up with their own model which has higher embedding dimensions. We still support that in Azure Document DB. No more like thinking about what would happen if. So we are compatible with all the models that are being released in the world today. And one other thing about Azure Document DB is you can do vertical scaling as well as horizontal scaling along with the storage scaling. So vertical scaling involves increasing the resources like vCores, virtual cores, and RAM of your existing nodes or shards easily. Horizontal scaling means you are distributing your data across multiple nodes, enabling support for larger data sets and higher throughput. You can also independently increase your disk size, which without altering the compute tier, or which gives you providing more flexibility if your data grows in the future. So let's go into the scale-up process in much more detail. Since Azure Document DB is built on scaling up process, we support scaling compute, which is vCores and RAM, and storage IOPS, disk size independently. You can increase or decrease your computer storage without service downtime or application changes. We have larger disk up to 32 terabytes and 64 terabytes per shard, and we allow up to 10 shards at a time. The architecture supports smaller compute, larger disk, depending on your workload. We also have horizontal scale out. When scaling vertically is no longer sufficient, you want to scale horizontally by increasing the physical shard count. Azure Document DB manages logical physical shard mapping, and the logical shards are mapped into physical shards and requests are routed automatically. Rebalances is handled behind the scenes. We do everything for you, and we go up to 10 shards at a time. And we are the only MongoDB compatible database with instant autoscale. So how it works is ensuring there's a peak demand. We are always sure that your database is running at the same time. Let's say there's a spike during a certain time of the month or a certain time of the year where you see a huge spike from your user using your website. So instead of like manually scaling up like the month before to make sure that you meet the user demands, we instantly auto scale for you. And if we see the demand has slowed down, we are gonna manually lower the compute based on your workloads. So your application is still running without that unexpected need that is going to crash the website. We ensure that all our users have instant auto scale. So customers will choose this right tier for their workloads and under provisioning and reduce the escalations and like budgeting. And since we are a first-party Azure service, you get all the authentication and access management, data protection, and network security built right in for no additional cost. We have database security in Azure Document DB with in-transit security, data encryption in transit, and at-rest security. So with a first-party Azure service, you get all the Azure requirements that you're looking for. And we also made sure migration is seamless for whatever workload you're looking at. We offer 3 types of migration. First, we have the offline migration. So think about it like a snapshot bulk copy from the source to the target. If new data has been edited after we start an offline migration, it's not going to be copied over. But for that exact reason, we have online migration, where apart from the bulk start copy activity is done in offline migration, a change stream monitors all the addition, updates, and deletion that has happened once the bulk copy start has been worked on. And it remembers all that information. And once that information has been migrated to Azure Document DB, it updates and deletes whatever the updates have been done when the migration has started. You can also cut over at any time when performing an online migration to ensure it remains active until manually finalized using cutover. So to prevent data loss, and only proceed with cutovers when the replication gap has been eliminated across all your collection. So choose the best way you want to migrate your data from your local or any other MongoDB compatible database to Azure Document DB. We have an excellent tool for this, where we have a VS Code extension where you just have to provide the connection string from your source to the destination, which is going to be an Azure Document DB, and you could just migrate your data without any interruption. Since we are MongoDB compatible database up to 99.03%, we will tell you if certain changes are required, which I don't think is going to happen, but we give you an assessment, a pre-migration assessment, which tells you what are at risk, what needs to be changed before you even start your migration. So you can have all the information you need before migrating your huge workloads from on-prem or any other provider to Azure Document DB. So since you have, let's say you are running through a migration and you have an issue migrating your data to the cloud to Azure Document DB, we provide free migration with Cloud Accelerate Factory. You can also reach out to the product team directly by just emailing us at cbdmigrationsupport@microsoft.com. And one of the people working on Azure Document DB will definitely reach out and make sure your migration is seamless and there are no other issues or data loss while you're migrating your data from on-prem to the cloud. So we give you all the tools that are necessary to migrate from your on-prem or from any other Mongo compatible database to Azure Document DB. But if you have any questions, feel free to reach out. And I think you should get started with Azure Document DB with the free tier, where we give up to 64 gigabytes of storage completely free. No credit card required to sign up. Just try out and see how you like it. Or you can even try our local instance, run a local Document DB server using a Docker container, or even checking out all the samples that we have built for Azure Document DB or Document DB by checking out the website documentdb.io/samples. And the demo that I showed over here is also going to be available over there. So if you want to take a look at the code, how it worked, all the information is provided over there. But feel free to reach out to us if you have any questions, or drop a question in the chat or in the YouTube comments, and we will make sure to be able to answer it. Thank you.
My name is Johnny Khalife, and I'm CTO with Southworks. We typically use Cosmos DB in the solutions we build for our customers as the operational backbone for cloud-native applications. It works really well for customer-facing platforms that need to handle real-time data like user context, configuration, and workflow state. We also use it a lot in distributed and event-driven systems where data is coming in fast and changing constantly. And that's where Cosmos DB really stands out. The main benefits we've seen are speed, flexibility, and less operational overhead. Cosmos gives you low latency performance, a data model that adapts easily as requirements evolve, and the ability to scale without having to redesign the system. And it's fully managed. Teams can stay focused on building and shipping instead of spending time running the database. The main outcomes have been faster delivery, consistent performance, and the ability to keep expanding without friction. We are able to ship features quicker, keep performance strong as usage grows, and add new use cases without having to rework the data layer. At the end of the day, it helps our customers move faster and scale with confidence.
Welcome back. And all I can say right now about what we've seen so far, amaze, amaze, amaze.
That's right, Jay. We've seen how developers are building across clouds and designing flexible systems.
Yeah, and you know what? We've heard back from some of our great members of our community who have left some things in the chat. So Shanola said, looks like there is a great future for Document DB. You know there is, Patty.
I know that there is. We're doing a lot of great things with Document DB, and especially with open source Document DB. So we're always available. And if you want to learn more about it, just visit documentdb.io. Also, we have a great comment about, from Bihan. Building real-time dashboards is a breeze using change feeds, and it really, really is.
Absolutely, yeah. And we heard so much great stuff from Justine today about the change feed and how it's really helping people with real-time applications. Yeah. But now it's time to go into some real deep content, things that we know are so important to having a well-created, efficient, and cost especially considered when we're talking about indexing.
Yeah, I couldn't have said it better, Jay. This is really where performance comes together in just an application.
Yeah, and if you want to revisit these sessions later, you'll find everything in the full playlist. It's going to be at aka.ms/CosmosConf26 playlist. It's in the chat right now. Go ahead and keep it linked, keep it bookmarked for later.
Yeah, I know that for me personally, we're so busy hosting. That's definitely something that I will check out afterwards.
Absolutely.
And if you have a minute, please, we'd appreciate your feedback. So if you want to share your thoughts, go to aka.ms/CosmosDBConf 2026 survey.
Yeah, we want to know so we can keep doing this show and making it great for you. So up next, we've got a really great one. It's called Querying and Indexing in Azure Cosmos DB, the complete guide.
Yeah, here's Dr. James Cadella.
Hey everyone, welcome to Querying and Indexing in Azure Cosmos DB. I'm James Cadella, Product Manager for Querying AI in Cosmos DB. Let's get started. So in this session, we're going to imagine a multi-tenant e-retail platform where we have customers that can shop across a portfolio of different products and outdoor brands. We're going to take a look at some common query workflows that such a platform might use in order to help their customers search for different products. Now, we're going to run the same queries against the same set of data, but we're going to compare it in two different ways. First is we have a container called products, which has no indexing policy whatsoever, and we're going to use some unoptimized queries to run these workflows. Next, we're going to run the same queries against an optimized collection that has the best indexing policies and using the best practices for creating queries in Cosmos DB. And we're going to compare the performance and cost differences. So what are we going to cover in this session? We'll start briefly on partition keys, what they are and how to use them. Then we'll dive into basic queries, queries that use a composite index or more complex patterns, handling array data in queries, geospatial data, computed properties, and finally end with our advanced search capabilities, including vector, full text, and hybrid search. Plus, we'll take a look at indexing metrics and query execution metrics to help us make sure that our queries are performing optimally. So in all of these different scenarios, we're going to see a few common patterns. First is we'll see an example of a query or two that is going to power the scenario. Next, we'll see the RU charge, so how many request units that query execution cost. We'll see the latency, or the time it took for the Cosmos DB container to execute that query. And then we'll see the indexing metrics. So this will show us which indexes were utilized by the query and what potential indexes could have added benefit to the query if they existed in the indexing policy. So maybe better performance or better cost or both. We'll also see query execution metrics, which show us exactly component-wise where the query took the most time and spent the most amount of work in the entire process. Now, what does our data look like? Well, imagine that we have a catalog of different products for our e-retail shop, and we have different products as data items. So you may have an ID, a tenant or a store ID. So this is the Ridge Supply Store, a SKU, a name for the product. So in this case, it's a camp stove, and a bunch of other metadata that you'd expect to see in a product catalog, along with a description, tags, some date timestamps, as well as GeoJSON data that tells us exactly where this product is located at that specific store, as well as an embedding field that contains a vector embedding that describes the description and name of the product. And we'll use this later on for a vector similarity search. So let's start with partitioning. Partitioning in Azure Cosmos DB determines how data is distributed and routed. Partition key provides a hint to Cosmos DB to which logical partition the data should be written to or read from. So in our scenario, we imagine that we have 3 retailers or 3 shops, and we're going to partition on that. So most of our e-retail queries can be scoped to a single retailer unless the user wants to search across the different retailers. Now, in general, a good pattern to use is queries should really include the partition keys whenever possible. This allows your queries to be routed to the exact logical partition or small set of logical partitions where your data lives. This helps you keep RU costs and latencies low and avoids potentially costly cross-partition queries. Okay, and we'll see an example of that in our first couple of queries. So let's start with the basic query operations, right? So when I say basic queries, we're going to use equality filters. So quality filters, range predicates, single property sorts or order bys, all these in combination to create a very basic, common query pattern. So for an example, in our e-retail shop, maybe we would need to filter on a category or do some simple sorts like sorting products by price. That's useful really every single sort of product grid or carousel that you'd see in an e-retail shop. And it's important to note, as we'll see, a query that returns the correct results is not the same as a query that scales. So we'll want to make sure that we're using best practices and the right indexing policy to make sure that our query can execute performantly. Okay, so I'm going to switch over here to my terminal. And the first thing I'm going to do is I have some sample runner here where I'm going to run some sample queries against my data set of about 10,000 different products. And so I'll go ahead and run this project and we'll get started. So we're going to see two scenarios. We're going to see a basic filter query and a basic filter plus order by query. So here we can see the example of the basic filter. So we're selecting a few of the different property paths of our data items, and we're adding where clause into conditions, right? So we're going to scope it to a particular tenant or shop, and then we're going to make sure that the category name is targeted to the category that we're really interested in looking for. So maybe this user really wants to look at camping tents and backpacking tents, right? So we're going to press enter and run the first query. And so now we're going to spin up our job and we're going to go execute a query from my laptop, hitting the Cosmos DB backend from my Cosmos DB resource deployed on the West Coast, and come all the way back here to New York and show me the results. And so here I can see the results for my query, and I can see a couple different products that came up. And as I scroll up here, I'm going to see a few things also, right? So here are the index metrics that we had talked about. So this first query is running on our products container that has no indexing policy whatsoever. So the index metrics says that it wasn't able to utilize any index, which makes sense because we don't have an indexing policy, but it was looking for potential indexes. So it was looking for a category name and it was looking for a tenant ID. So these are both things that we filtered on in the query itself. And the index impact score is high. So if we add these to our indexing policy, we're really going to get much better performance and better RU cost characteristics as well. Scrolling up, we can see the query metrics. So this tells me how many documents were retrieved, what the size was of all those documents, and other metadata that helps me understand the total query execution time or where the query spent a lot of time in processing. And then I also print out some summary metrics, like how many rows were returned in this query. So 136 match the query filters, and then the RU charge. So 343, almost 344 RU. So this is not a cheap query. Okay. So let's go and run this on the optimized container now. So we'll now run this on the container that has an indexing policy that will make this query more performant. And we can see the same results come back. And this time in the index metrics, we see that it was able to utilize the indexes that are now in the policy. And there are no indexes that were not in the policy that it was looking for. So that's great. So we're effectively using all the indexes that we can. And we can see that the RU charge is significantly less. Actually, let's do a side-by-side comparison. So we can see that without the index, it was about 240 milliseconds of execution time for this query. With the index, about 38 milliseconds, so more than a 6x improvement on latency, and then more than a 7x improvement on RU charges for this query. So really demonstrating the power of having a proper index, even just with a simple filter with just a couple of query where clauses in the query. Okay, so now we're going to run a basic filter and an order by clause. So we're going to go ahead and run this, again, using our .NET SDK, running sort of a default query. And we get back that this error actually wasn't able to operate because it was looking for an index to do the order by on the container itself, and we didn't have that there. So let's go ahead and do the same query on the optimized path. So on the optimized collection, where we actually do have the indexing policy, it was able to leverage the indexes. And actually, it's telling us that I forgot to add a composite index here, but we'll see an example of that maybe next. So we can see that it was able to execute. It's actually relatively performant. Comes back, 27 milliseconds of query execution time. That's a pretty fast query. All right. So now let's go back to our slides and we'll go to the next scenario, right? So we saw basic query operations with filtering and order by clause. Next, what we'll do is look at composite indexes, right? So composite indexes are really useful when I have where clauses or filters that cover multiple different properties and or an order by with multiple different properties in the order by as well, right? So adding complexity to my queries really makes composite indexes a really useful pattern for me, right? So maybe if I'm searching through my product catalog for the latest backpacking tents. So I want to search for some keywords, and I also want to have an order by clause in there for the most recent items, or I want some price order by along with my query filters. There's really great use cases for composite indexes. And the composite index needs to match the order and the sort direction in which you're going to leverage it in the query. So that just keep that in mind. And of course, you have to add composite indexes that's not indexed by default in Cosmos DB. Okay, so let's clear our screen here. And what we're going to do is we're going to go run the demo scenario with composite indexes. So let's spin this up. And if you're curious, this tool that I'm using in the terminal, it's going to be available on GitHub. There's actually a link and a QR code at the end of this presentation. So don't need to bother taking notes or anything like that. You have access to all the code at the end of this talk. Okay, so we're going to test a couple different scenarios here. We're going to look at composite equality and range filters, and then we're going to look at composite filtering and composite sorting in the same query. So in this example here, we're going to select some properties, and we want to make sure that we're scoping to a particular shop and scoping to a particular category for those products, and we want the price, to be greater than something, right? And so that something's going to be 100, so 100 US dollars, right? And so let's go ahead and execute that query. And again, with all these scenarios, we're first executing on the unoptimized collection, with the collection without any indexing policy. And we can see that the results come back. Maybe it took some time for us to run. We can scroll up and see the metrics, and it took about 350 RUs to execute that query, which is not cheap. And we'll go and run this on the optimized container, and it's going to execute much, much faster. And we're going to skip directly to the side-by-side comparison. Look, there's no contest here, right? 13x, more than 13x improvement in server latency, so query execution latency, more than almost 8x improvement in RU charges. It's no brainer that you want to use composite indexes for these sort of complex query filter scenarios. Now, when we compare in the next scenario using a composite filter and sorting, we'll have sort of the same issue that we saw last time, right? For composite indexes, for composite order buys, I really need a composite index to be able to execute that effectively. So we're not able to execute this on our container that has no indexing policy whatsoever. But when we run this on the container that does have the indexing policy, not just the standard indexing policy, but also our composite indexes, we're able to realize that it's still incredibly performant, right? 16 seconds. It took 16 seconds for this query to run on over 10,000 data items. And it cost about 47 RUs, so much, much cheaper than we would expect for any of these operations if we're not using sort of an optimal way and best practices of leveraging composite indexes. Okay, so let's talk about the next area. So we covered basic queries and composite indexes. Now let's jump into arrays. So Cosmos DB can index the content in an array. And then you can use query functions like array contains, or you can reference certain positions of the arrays, or you can even do these joins like intra-document joins, and you can use exist subqueries and all sorts of great functions to resolve from the index instead of scanning every single document for the contents of those arrays. Right? So for example, maybe my products have different tags, like a waterproof tag or a tag on what seasons that product can be used for. And these tags can power, filter navigation. So imagine that a customer is searching for products and they want to filter by other categories or other characteristics in this product catalog. The important thing to know is that, Cosmos DB is schema-free, right? It's essentially JSON documents. So instead of joining data across different entities like you would in a relational database, joins occur within a single item. So there's scope to that item. You don't do cross-item or cross-container joins. It's really meant to sort of bring up and interact with the objects or items that are contained within an array. So let's see an example of this. So we will switch back here to our terminal. And then we're going to run the demo scenario for arrays. Let's go ahead and load this up. And so we're going to test two different scenarios. So we'll run in a scenario where we're leveraging the array contains properties. We're searching an array to see if it contains some specific value or object. And then we're going to see an example of join and how that can be used as well. Right. So in this example, maybe we're filtering on the tenant and we want to make sure that the tags array contains a specific tag, like waterproof. So we're going to go ahead and run that without any index whatsoever on our products collection. And we'll see the results that come up. And we see the results. And of course, we see that it was looking for indexes that it couldn't find in the indexing policy because there is no indexing policy. And we can see it took about 411 RUs to run. So we'll go ahead and run this on the container with the index defined. And we'll see that the same results come up here. And we'll see that this is actually a much, much cheaper and efficient query, right? So we did use the indexes that we have defined. And it cost, significantly less RU. So let's do a side-by-side comparison. So over, 1.4x improvement in latency and over 3x improvement in RU charge, right? And these performance gains that you get from adding the index only grow when the size of the data grows, right? If I had instead of 10,000 plus documents, if I had 100,000 or a million or 100 million documents, right? You could imagine that the improvements that I'm seeing here would actually be many-fold more than what I'm getting just from like this small scenario. Next, let's see an example of join. So we have select of a couple of properties like our name and description, and then also the tag, right? So we're getting the tag, we're getting tags from the c.tags. So c.tags is the array of different tags for that product. So we're scoping again to the tenant ID, and we're looking for a particular tag. So this time we're going to, again, look for waterproof as a particular tag using join syntax. So again, we're going to run without the index. And then once this executes, we're going to just go right ahead and run it on the optimized collection that does have indexes that were, that we chose specifically, or that actually, to be honest, this is the standard indexing policy, right? By default, Cosmos DB indexes all the properties by default for range and inequality filters. And so I actually don't need to add anything specific for array operations here. The one in the queries that I'm showing you, like this is part of the default indexing policy. And so we can see that without the index versus with the index. So with the index, you get over 5x improvement on latency and over 3x improvement on RU charge. So again, just demonstrating the power of having an index policy for my arrays. And now what we're going to do is we'll move on next to talk about computed properties. So computed properties, what you define derived fields from query expressions on the container properties. So they're not materialized at read time or query time. They're not computed at query time, but they're materialized and indexed at write time, right? And the properties aren't persisted in the items themselves, which is makes it really nice for efficient storage, right? So imagine that in our product catalog, imagine that we're storing, the different category path in a sort of compound string. Like maybe our string is camping and tents and backpack tents. And what we want to do is maybe we want to filter on some subset of these, right? Some subset of these categories that are stored in a string. So without a computer property, maybe I would write a query that separates these out at runtime in the query itself. And that could lead to, when I'm doing a lot of queries, I'm just doing that operation over and over and over again in the query, which is not the most efficient way. So in a computer property, I can do this, I can write it once, and then I don't have to worry about it at query time. And it's important to note, computer properties, like you have to define these yourselves, and they need to be explicitly added to the indexing policy. But once you do this, then you can reference them just as you would any other property in your document, except they're not a property of your document. They're a computed property. So let's see what that looks like. So we'll go back to our terminal, and we'll clear the screen. We'll go ahead and run this computed properties workflow. Okay, so a bunch of stuff's popping up here. So we're going to look at a derived field lookup. So here's the query that we're going to run without computed properties. We want to project a couple different properties of the products. And then, of course, we're going to scope to our tenant or our shop. And then we have in addition, we have this additional part of the where clause where we're going to look at the category name, and we're going to take a substring and take the first element of it. We're going to trim this as well. And so what we're doing is we're basically getting the first category that's listed in that string, right? So, and we're going to call this the primary category. So maybe the first category of this product is the most important. It's the main category of this product. But unfortunately, all the products categories are maybe, because of my data model or the way that my application is designed, it's stored in a way that is in a string rather than an array. And so maybe I want to search for in particular just what this primary category might be. So without computer properties, this is what my query would look like. With computer properties, I can actually just reference a computer property that I create, and I can reference it like any other property in my document. c.cp_primary category. And what I can see here is when I define a computer property on my collection, I can give it a name. And then basically I can give it a query that defines a computer property, right? So the logic that we had here that was previously in our unoptimized query is now in a computer property. So now this can compute it and store it in the index and makes it really efficient for search and retrieval. And I don't have to rewrite this in every single query. I don't have to rerun this logic every single time during query execution. So it should make our queries more performant. So let's go ahead and run this. So we'll run without the computer properties. We'll go ahead and execute again on our product container. And again, so we're going to actually, so in this example, we're actually going to show the difference between a computer property and no computer property. So we're still going to leverage the index in both of these scenarios, but one time we'll be using, in this first one, we're not using computer properties. And then, and so we can see the characteristics of this. Right, so we can see it's 378 RUs. And then in this optimized version, we're going to be using the computer property itself. So again, the first query did not use computer property, but it still used the indexing policies. Now in this second run, we're going to use the computer properties and the index computer property as well. And we'll look at the side-by-side comparison. Okay, so the execution time of the query was 88 milliseconds, 88.77 milliseconds with the computer property. So over 3x performance improvement with computer property in terms of latency, 1.45x improvement in terms of RU charge. And again, as your data set scales, this benefit only increases. So really, really interesting application of computer properties here, right? It's a really great feature that if you're doing this complex logic over and over again in your queries, you can really simplify your workflow and get better performance out of your queries by using the computer property. All right, so what do we have next? Geospatial, great. Right, so geospatial data enables you to do all sorts of cool filtering or bounding or sorting by physical distance, right? By having locations like longitude, latitude locations on Earth. And this allows you to use all sorts of complex geospatial functions that we have in the Cosmos DB query syntax. So in this example, we're going to use the ST-distance function. So a common example that you find in e-retailers, right? You are looking for products and you want to make sure that maybe you can find a store nearby that has this product in stock that you want to go pick up, right? And again, spatial data here needs to be valid GeoJSON. And of course, you need to add it to your indexing policy by default. Cosmos DB doesn't index geospatial data, but it's really simple just to add it to your indexing policy wherever you're going to store whatever property you're going to store your GeoJSON data. Okay, now let's see this in practice in our demo code. So first, we're going to clear a terminal. So we'll go ahead and do that. Then we're going to go and run the geospatial scenario. So what are we going to take a look at in this scenario? Well, we're going to look at a couple of things. So first, we're going to do this distance filter. So maybe in this scenario, we want to make sure that the product that the customer is looking for is in stock in a store that's close to them, right? So we are going to have a couple of things in our query, right? So we're going to project the ID, the name, the description, and the distance, or the geospatial distance as this distance meters alias. And then we're going to have a where clause on the tenant ID. So we're going to look for a specific tenant or a specific shop. And then we want to make sure that it's within this maximum distance. So we want to make sure it's within, say 50 kilometers of our user. And then we're going to order by ST distance, right? So what this is going to do is going to rank the results in order by their geospatial distance from the user to the stores. So let's go ahead and run this query. And we're going to run it, again, first without the index. And we can see some of the results that come back and some of the characteristics. But let's just skip this and we'll go ahead and run it with the index. And then we'll look at the side-by-side comparison. So side-by-side comparison shows something really interesting, right? Without the index, we see about 89 millisecond of execution time on the server. With the index, 55.88 milliseconds. So it's a 1.61x improvement with the index. And then, of course, the RU charge as well. We get a 2.34x improvement on RU charges, right? And again, this only increases, right? The improvement level only increases as the scale of my scenario. So the more data that I have increases, especially if I have really high throughput account or account with lots of different partitions, right? So we get a lot of benefit by using the index and also by specifying the partition key in that where clause as well. So now that we talked quickly about geospatial, let's look at some of our search capabilities. So vector, full text, and hybrid search. Let's start with vector search. So vector search uses vector embedding and our vector distance function combined with a vector index. So in Cosmos DB, we have multiple vector indices, including disk-ANN, which allows you to do semantic search with very high accuracy and low latency, really at any scale, even up to billions of vectors. So imagine that a shopper wants to search for something, in a product and uses some, text phrase, right? Like lightweight tent for rainy hikes. So the vector search will allow us to find semantically related products, not just products that match these keywords or phrases. It's important to note, so vector search is really good to add a vector embedding policy and vector index. So you could add like a disk-ANN index. And if you want to do multi-tenant search, like for example here, if I wanted to search specifically on a particular tenant or our particular shop, I could shard our vector index to that, by the different shops or tenant IDs. And so I could isolate my vector search just to those shops and I can get really performant tenant isolated search that way. So let's see an example of vector search in practice. Okay, so we'll clear the screen again. And we'll do a run of the vector scenario. So here our query is very straightforward. We're selecting the top 5 most similar items, and we're going to project the vector similarity score. And then we'll also order by the vector distance, right? So we'll order by the vector similarity score from most similar to least similar. And we'll run it with and without the index. So we ran it with and without the index. We'll skip right to the comparison. And we can see the server time. So almost 24, almost 25x improvement in server-side latency using the vector index compared to not using a vector index. And then the RU charge is also much, much lower, right? Not even 16, 15 RUs on vector search on over 10,000 documents. So really, really performant using that disk-ANN vector index. Going back to talk about full text search real quick. So full text search uses different linguistic analyzers, so tokenization and stemming, and functions like full text contains and full text score to match and rank documents by keyword relevance, right? So if I want to make sure that certain products contain a certain phrase or keywords, I can use full text contains. If I want to search for items using this BM25 scoring, which is a measure of a frequency of whether these terms are in the documents or not, I can do an order by rank full text score clause as well. So we'll see examples of that. Right. So an example here is when a customer wants to do a search and you want to search by those text keywords or by those text phrases. This is a really powerful tool for enabling that. Okay, so we'll run this scenario as well. So we'll clear a terminal again and go ahead and run the full text demo. So here's what we're going to test: the full text contains and full text scoring using BM25. So we'll do a simple query here where we have, we want to make sure multiple terms are contained within the products that we are looking for. So we want to make sure that it contains waterproof and conditions and windproof. And so we're going to run this without any index whatsoever. And then we'll run this with a full text index defined on that collection. And we can see that, it's 2.3x more performant and uses far fewer RUs. And again, the difference here, the benefit only increases as your data size scales. Next, we'll run the full text scoring, right? So what we're going to do is we're going to search for these items, and we're going to order by their BM25 score. So how relevant the products are by how often these keywords appear in the descriptions or the names of these items. So running without the index versus with the index, a 30x improvement in server latency using the index, and a 116x improvement on RU charge by using the index, right? So this really demonstrates that we're able to really effectively use the index once we do these advanced search or ranking methods for lexical or full text search. The index is incredibly powerful for doing these very efficiently at scale. And finally, we have hybrid search. Hybrid search combines multiple different measures like vector similarity and full text scores into a single ranked result. So for example, if you want your shoppers to be able to make sure that maybe your searches contain certain keywords, but you also want to capture the semantic similarity from vector search to find related products, hybrid search could be a really great approach. And again, you have to define both the full text and vector index to utilize this. And then the RRF function merges the two scoring methods together. Okay. So we'll clear the screen and run our final demo scenario here. Okay, so we're going to see an example of the hybrid search. So we're going to select the top 5 items from our product catalog, and we'll also project the vector similarity score. This time, we're going to order by rank. We're going to use the RF function to fuse together results from full text score and from vector similarity score. And then we're going to do this without using an index and with using an index. So we'll go ahead and run this first without using the index. And then we'll run this again while using the index. And side-by-side comparison, we see that the server time, 1.13x, so faster, and then RU charge is 2.8, almost 3x cheaper to run, right? And again, these improvements, the server time looks relatively modest, but you have to keep in mind that this is just on 10,000 data items, as I keep mentioning. As the size of your data set grows, benefit of using the index also increases. The benefit of scoping to a particular partition also increases, right? Especially if you're using any sort of search like vector similarity search or the hybrid search, right? Our vector indexing algorithms allow you to search in a way that scales sublinearly. So as your data set grows, maybe your data set grows, 200 times in size. Your vector similarity search won't even increase by 2x in latency, right? It's that efficient. It really scales sublinearly with the size of your data. So keep that in mind that, as your scenario grows, as your e-retail shop becomes more and more popular and you have more and more products and deal with more and more customers, you're going to really reap the performance benefits of using proper indexing techniques and query techniques. Okay, so that's all we have today. There's some references here to get you started. All the material from this session, including the slides and the code examples that I ran, along with the sample data, are available at aka.ms/cosmosdb/conf26query. If you're interested in learning more about anything we talked about here, whether it's queries, vector searches, full text search, hybrid search, there's also some great Learn documentation to get started. And we also have a QR code that if you want to scan that with your phone or scan it with your browser, and it'll take you immediately to the GitHub repository where we have all this content available for you. All right, that's it. Hope you enjoyed the content. Thanks a lot, folks. See you next time.
Hi, everyone. I'm Jess Ramos, or you might know me as Jess Ramos Data Online. I'm the founder of Big Data Energy, and I create data and AI content for over 500,000 followers on social media. Right now, everyone's talking about how good AI is. Which model's faster, smarter, cheaper. But for me personally, I can't stop thinking about the data. We've all heard the saying, garbage in, garbage out. And this has never been more true than it is right now. Because you can have the most powerful model in the world and still get completely unreliable outputs if your data layer is not solid. AI doesn't run on neat structured tables. It runs on vectors, documents, and real-time streaming, data that's messy by nature and massive by scale. And that's exactly where NoSQL shines. We're talking AI search, real-time personalization, RAG pipelines, and agentic apps that need to read and write data fast. And this is the stuff that actually breaks your infrastructure if it's not built right. Cosmos DB is built for exactly that. Global distribution, single-digit millisecond latency, and both operational NoSQL and vector data. And I'm so excited to keep learning more about this at Cosmos DB Conf. Thanks so much for coming, and let me know on LinkedIn what you learned today. Bye!
Hey, welcome back. We are so glad you're here with us. We've had a great start. Whoa, we got about an hour to go. Wow.
Yeah. Thank you so much for sticking around. And we have so much more to show you, as well as just the on-demand sessions.
And you know what? We've seen so many things, so many demos, and to help us move along, we've got another amazing live session with none other than Andrew Liu. You might have seen him earlier today.
Yeah. Andrew's going to help us learn even more about how Azure Cosmos DB works under the hood. Andrew, welcome back to the stage.
Cool. Hey, nice to be here. Hey, everyone. We're going to do a bit of an experiment. We're going to do a whiteboarding session, and we're going to go right into this. So, have you ever wondered what happens when you create, when you go to the portal, you hit create Cosmos DB, and just what happens behind the hood? That's the intention of this session. And so let's start with our SDK and taking that perspective from this point of the view of the world. So the SDK is going to be embedded either in an application, or even when we build things like the Azure portal, we view that as a client from the database's perspective. So think of this as the app or the portal. This is wrapping our SDK. We actually have multiple flavors of the SDK beyond just programming languages. We have a management SDK as well as a data plane SDK. And what ends up happening is when we do from a client-server perspective, behind the scenes, what this is going to go and talk to is a control plane and a data plane. And we're going to think of these two things as very separate. The control plane is going to be wrapped over ARM. Oops. This stands for Azure Resource Manager. And so whenever you make REST calls over into a DNS that looks something like management.azure.com, what happens behind the scenes is you can think of ARM, one mental model is like a big reverse proxy. And that reverse proxy, when it goes, hey, okay, you want to create a Cosmos DB or add a region or fail over to a different region or scale your RUs, what that's going to do is it's going to go route those requests into what's called a resource provider. And so Cosmos DB has a resource provider, and of course, every other Azure service out there also has its own resource provider. And ARM's job is to go and route to the correct resource provider. Now, on the data plane, this is going to be a different DNS entry. This is going to be cosmos.azure.com. And the data plane is responsible for what you think of a database actually does, right? This is going to be writing your data, indexing it, and then making it available for fast, efficient queries. And so when we go and look at that path, all of these requests will first flow into our front-end server in Cosmos DB. We like to call this our gateway. And the gateway's job is to do request routing, because what happens is we have a distributed backend behind the scenes. And in the backend, what this will map to is effectively big clusters that we run behind the scenes. They are multi-tenant federations or clusters. We like to use those words interchangeably. And within those clusters, this is going to be the deployment model in Cosmos DB. So if we go look from a physical to a logical mapping, on the logical layer, you're making this thing called a database account, down to a database, down to a container. And I might use different words like container or collection interchangeably. Container, we kind of use that as kind of the API agnostic way of saying that. And then depending on some of the Cosmos DB APIs, you might have seen the word collection, especially for any of the document-oriented data models. And within that, we store our data. Everything within this container is what is being powered by the backend on the data plane. And behind the scenes, what this container is it's not a single server, right? Like what we're doing is we're stitching together replica sets. So think of I have a little replica set powered by Service Fabric. where I have a primary and a few different secondaries. And each of these is a database replica. And a database replica is going to be the core building block for what's powering the software behind the scenes. This is going to have the query engine, it's going to have the indexing layer, it's going to have the storage. And beyond just doing the bread and butter of what a database does, it's also going to have other things like admission control, and that's where we're going to have things like our resource governance. So think of this, what we're doing is we take this software, we stitch it together into a replica set, and on that replica set, this is what's going to form a physical partition. And what happens is when you scale a container, we're going to create one or more physical partitions. Each physical partition today is able to support up to 10,000 request units per second worth of bandwidth. It's also able to support up to 50 GB worth of storage. And so when we talk about infinite scale, like millions of RUs, what we're really doing is we're just taking that container and we're sharding it aggressively, where we're creating tons of these different physical partitions behind the scenes. Now, these get placed onto these big federations. So back to from a federation perspective, think of this as in the data center, I have a bunch of racks. Each of these racks are going to have some shared infrastructure, like a top-of-rack network switch. And we can also think of those in terms of helping us compose what will become a set of fault domains or update domains. And so when we set up these federations that go and host all these different database replicas, what we're doing is on these different nodes, think of these nodes as basically spinning up these replicas and having them on standby. And so when you go through the control plane saying, hey, I need to go scale my Cosmos DB, give me some more RUs, behind the scenes, what that resource provider is doing with our control plane is saying, hey, this workload needs to scale, I need some more partitions. Do we have some bindable partitions? Let's go take a look at this federation. We might have a replica stitched together across different fault domains and update domains. And so let's say I have a couple of different nodes here. We're going to stitch together a replica from each one of these into a bindable partition, and we're going to give that partition over to that container. Now, these federations, don't think of as an account as having to live on a single federation. We span across many federations for infinite scale. And why we do that is we decouple the physical and logical layer, and this allows us to always stay current on our hardware. Speaking of the hardware, this is a nice shout out to our sponsor, AMD. We use, especially in the newer generations of our federations, a massive amount of AMD CPUs. Why we love the AMD CPUs is because they're incredibly power efficient. They give really good watts for the unit of compute that we give, as well as that helps us drive the cost down. And as we drive the cost down, this is what we're also able to go and turn that into cost savings for our users like you in the form of new features. So things like the dynamic auto scale, the RU pooling with the new Cosmos DB fleets, the Cosmos DB serverless. Those effectively what we're doing is we're using elasticity to for the TCO of operating a database, right? Every workload is going to be bursty. Any transactional workload is like that. And what we're doing is we're passing all of the savings we get from the AMD into nice elastic features for our users. Now, on the federation, as we go and stitch together these replicas, we can jump into our first, I think, bigger, meatier topic. And that is going to be how we look at the partitioning. So Cosmos DB uses a technique called consistent hashing. It's a fairly ubiquitous concept for any kind of sharded database. It tends to be the industry standard. And I'll kind of walk through that in terms a little bit just to help understand it and compare it to what maybe folks will think of as like a naive hash. So in a naive hash, think of it as I'm going to go partition my data, and behind the scenes, that container now has a ton of these physical partitions, right? Like a container has let's say 50,000 RUs. We know each one can support 10K each. So this is going to go and create 5 of these physical partitions behind the scenes. It's going to go then route, let's say, some data onto this node, some data over into this, or this physical partition, this physical partition. How does it know and to deterministically route, right? Like if I go and query for, let's say, Alice's data, in a user-based system, I need to be able to actually hit the partition hosting Alice's data. Otherwise, when I do that query, I'm not going to find anything, right? And so what happens is we ask Hugh for a partition key. And so let's put in some values here just to give you an idea of what is happening. So we have a logical partition key. This is the partition key that you're supplying. And that's going to go hash to some numeric value behind the scenes, right? We can use different hashing algorithms. In this case, Cosmos DB uses this algorithm called murmur hash because it's very compute efficient. And let's look what happens if you do a naive hash, right? Like in a naive approach, let's say if I only had 2 partitions, the challenge you're going to run into in a naive hash is if I, let's say, go and let's say mod 2, well, what I'm going to see is a distribution that looks like 1, 2, 1, 2, 1, 2. Now, what happens if I need to grow that on an elastic workload? I'm scaling that over to 3 partitions. And right away, you're going to go see what the problem is and why a consistent hash is so valuable. So when I do a mod 3, right, I'm going to get a distribution that looks a little bit more like 1, 2, 3, 1, 2, 3. And notice what's happening here. If I am mapping data, let's say Alice, Bob, Carol, let's see, put Danny, Eve, etc. Notice this challenge where if Danny mapped to partition 2 when we mod 2, but now maps to partition 1, we're doing effectively a huge shuffle, right? A lot of data would have to go from the second partition into the first, from the first into the second, from the first into the third, the second to the third. That's not very efficient, right? And so this is why a consistent hashing scheme is a much better way of doing this rather than a naive hash. But this will give you the intuition in terms of how this works out. So a consistent hash you can think of as a range partitioning on top of a hashed-based scheme. So if I go and think about the hash values, where this is the min value on a number line, and I do this as a circle, since everything is going to go map onto this ring. If I look at min value on where it hashes to 0, 0, 0 to FFFF, if I have 2 partitions on day 1, then the way of scaling this is actually very easy on mapping. What we can do is we can just go chop the number line, right? And so from 0 to approximately half, and then from half to, let's say, +1 over to max value, I can go map this into physical partition 1, and this can go map to physical partition 2. Now, what's neat here is in a consistent hash, rather than doing any of this shuffling, what happens if the first partition is filling up? Or what happens if the second partition is filling up? Well, then we can go and dynamically allocate more partitions by splitting them. And so what happens is, let's say I need to do a split, where I need to go and map now a third partition. So we can go from 0 to, let's say, quarter, and then quarter to quarter +1 over to half. Well, notice that I can now relocate, let's say, or not even relocate any data. I can just go and on the hash values directly, if like Alice was here, Bob was here, and Carol was here, rather than having to shuffle things around, I can just say, hey, Alice and Bob used to be co-located on partition 1, but partition 1 has now turned into partition 1, let's say prime, and partition 1 double prime. And all we've done is split that data. And what's awesome about this is Cosmos DB can do this as an online operation where we'll handle the splitting or merging of the data on allocating the partitions, and then dynamically cut over whenever you need to go and perform one of these operations. So what Cosmos DB does is really the runtime aspects of partitioning so that you have auto partitioning. And really, as a user, what you're left with is the design time aspect, which is choosing a good partition key. And this is why it's so important to choose a good partition key, because ultimately, if you're partitioning, let's say, by a user ID, then what we're doing is we're using that user ID to go deterministically route which piece of data, let's say Alice's piece of data into partition 1 prime, Bob's data into partition 1 double prime, and Carol into partition 2. Now, this is one aspect of scale out. This is the partitioning aspect. The other thing I'd like to cover is the replication side. And what replication is really there for is a little bit different, right? Partitioning is what gets you ability to scale your request traffic. In particular, it does really well at scaling your write traffic. It can also scale your read traffic, right? If I have millions of QPS, well, I cannot have an infinitely number of CPU on a single box, on a single VM. There's still the physical aspect of it, which is put you on more computers. And so what we're doing is we can power many, many CPUs as long as we divide that data set and partition it out. Now, what replication is doing a little bit different is copying that data. Copying that data gives us two different things. One that's similar and one that's very different. The similar thing is going to be, it's one way of scaling your read throughput. The other thing that it can do is it gives you a lot of redundancy. And this is how Cosmos DB gives you 5 nines of availability. And we can think of this in multiple grains. So let me go and get some board real estate. And on the replication side, when we zoom in on any of these partitions, remember what we have is a replica set. And what we're doing is we're using a concept called quorums or quorum replication to go and provide that availability. Now, how we do those replica sets is going to be a little bit different in terms of within a region versus across region. When you do across regions, what we're effectively doing is we're spawning another partition in each of the different regions. And then what happens is we can have multi-write regions. What happens is one of these secondaries will get designated as a forwarder. We might have 3, we might have 4. This is a bit black boxed, but what we do is we dynamically size a quorum across a replica set, and this can be in, let's say, region 2. This can be in region 1. And within a region, we rely on Service Fabric heavily to do the within a region replication. And what's beautiful about this is it handles a lot of the things like leader replication for us. Let's say a primary is going down, whether it's willingly, intentionally. Let's say we're deploying a database software update. Have you noticed like Cosmos DB doesn't really have maintenance periods? It's just always online. You've never seen us say like, hey, it's time for a Windows update or it's time for an application update. That's because behind the scenes, what we're doing is we're just dynamically changing, oh, okay, let me take down a replica that's on a different update domain or a different fault domain, and let me designate and promote one of these secondaries over to a primary, and then shift that traffic over. What we're doing is we're live doing rolling updates, and that way when this replica is brought back online, what we can do is we're just dynamically writing to a rolling set of replicas behind that replica set. Now, what a quorum is a little bit different from your traditional primary versus secondary replication. In a traditional database, like let's say a relational database, what you're typically working with is either synchronous or asynchronous replication. And those come with pretty steep trade-offs, right? Like when you do synchronous replication, if your goal was high availability, if the primary goes down, that's fine. You can go and fail over to a secondary. But it actually goes and has some risks as well. What if the instead of the first failing, it's the second one that went down, right? Well, if you're synchronously replicating, well, even if the primary is healthy, now I have to go and cut that secondary in order to restore work back onto, bring the right availability back. And so what synchronous replication is doing is it's giving you really strong consistency. And in terms of disaster recovery terms, what you're really prioritizing is a low recovery point objective, right? Like if I go from the primary to the secondary, since everything was synchronously replicated, if I wrote to the primary, I know it's in the secondary, so I have a recovery point objective of effectively 0. Now, where synchronous replication is really bad at is the recovery time objective. If you are having to coordinate a failover, failovers take time, and so this is where you're going to be less happy as opposed to more happy. And then asynchronous is the exact opposite, right? In an asynchronous model, what you're going to see is your recovery time objectives. Well, hey, if the secondary fails, that's fine. I can just keep serving out of the primary. I'll just let the secondary lag behind. But how far is it lagging behind? If I do a cutover to the secondary, is the data that I just wrote even there? And so what you're going to see is the recovery point objective is going to be, well, it's an eventually consistent model, so you're going to have a lack of consistency, but you're trading up the recovery time objective. Now, where quorum replication innovates on this is rather than thinking of the world as, hey, let me just have one additional redundant copy or n number of redundant copies where I have a primary secondary model, what I can do is I can always write to a quorum of replicas. So imagine that if I have 4 replicas here, a majority quorum would be something like writing to at least 3 out of 4 of those replicas. That means that if any replica were to fail, in this example, let's say this fourth replica bombed out, and I was able to write to the primary and to these secondaries, or even if that primary dies, we go and promote one of the other replicas to be the new primary, and we get 3 out of 4 on the new topology. Any node can fail, and we're able to maintain that availability. Now, on the read side, this is what is really interesting, is if I go and circle any 2 replicas, right, I can do a minority quorum. Well, because I'm allowing fault tolerance for any replica to go down on the write path, on the read path, as long as I read at least 2 different replicas, I can still guarantee strong consistency, even though this is in a fault-tolerant system where I allow a replica to go down, right? Like, I'm always going to have replica overlap. If replica D goes down, well, A and B will, of course, both have the data. B and C would both have the data. C and D, the D would miss, but the C would still, because it's further forward in time, it's always going to win that vote, that you're able to get strongly consistent reads in the midst of a downed replica. Now, that's what we're doing within a region. And then across regions, what we do is we designate one of these secondary replicas to go and replicate over to another region. There's some slight caveats to that, depending on whether you're using strong consistency versus any of the other Cosmos DB consistency levels. If you're using any of the weaker consistency levels, you can think of it as we're doing an asynchronous replication over to the secondary region, and this is what gives you, higher availability, faster RTOs, at the trade-off of consistency. Or if you're using global strong consistency, what we're doing is you can think of it as synchronously writing to multiple regions. Now, there's a bunch of more things that go into that. For example, we can do dynamic quorums where if we have a third region, we can vote 2 out of 3 regions to give you even strong consistency that allows a region to go down. And what's really cool is Cosmos DB allows, it's not a single primary system. We're able to put primaries in each of these 2 different regions. And so on the SDK side, you never have to really wait for a failover. If you're in any of the weaker consistency levels using multi-region writes, if I'm writing to region 1 and region 1 goes down, that's fine. The SDK is actually smart enough. When you set in the, when you instantiate the SDK, you have that connection policy. You can set what the preferred location is. What it's doing is it's going to do a live redirection to the secondary region without even waiting for a server-side failover. And this is how you can collapse that recovery time objective down to 0. And with even in a strong consistency manner, we're able to go and minimize the RTO, where we now have the ability of doing fast failovers in a strongly consistent setup. We are very happy about, recently we had launched per partition automatic failover. What it does is, rather than looking at, hey, if one partition's unhealthy, another partition is healthy, and trying to have a live ops team go, hey, should I fail over, should I not fail over? That tends to be the bottleneck for any failover. We don't have to go and do any decision making. In a strongly consistent system with PPAF, what we can do is we can also then trigger that one partition to independently trigger a failover in this big distributed database without having to impact all of the other healthy partitions. And so this is how we're able to go and try to give you just softer trade-offs rather than thinking of the world as extremes in terms of eventual or strongly consistent systems with like, hey, do I want RTO or RPO? You can get both by using quorum topologies for replication, and then doing a lot of magic around redirections. Now, a third thing I want to go and show you that I think is good for every developer to understand in Cosmos DB is the resource governance aspect, right? Like when you go and create a Cosmos DB container, you're going to see like, hey, what is this thing, request units? This is what allows us to go and do pay-per-request models around serverless. It's what allows us to give you guaranteed throughput. Rather than just best effort, hey, we have some nodes with some cores, we're able to give you predictable performance. And so what happens is each of those replicas, when I look at the replica, where behind the scenes you can think of it as we have a resource governor, and you can think of that as like a token bucket algorithm, right? If you haven't seen token bucket algorithm before, think of it as like a bucket of tokens. And the request units are those tokens. When you go and do a database read, a 1 KB read is actually the baseline charge. That's one request unit. What we'll do is we'll take a token out of the bucket, right? So we'll subtract one request unit. And then on the resource governor, in order to go and say, hey, is the system overloaded? Is it not overloaded? We want to give predictable latency. Let's try to avoid anything like overly saturated CPU. What we'll do is we'll govern that based off of the relative CPU, memory, and I/O footprint of that request. And so each second, what we're doing is that we're then replenishing those tokens back in on a timer interval. And as long as I have greater than 0 RUs, we're able to keep serving requests. Now, one innovation that we had that's a bit new is the RU pooling functionality that we did with the Cosmos DB fleets. So what happens is we have one of these token bucket resource governors on each individual replica. So on that partition, right, so I have a partition, the RUs right now, first is a shared nothing counter. We have this on each individual replica. This is now a partition. And then we go and divide that evenly across partitions. What happens if I have a hotter partition and then I have like, let's say a colder partition? Can we go and donate budget from a colder partition over to a hot partition in a responsible manner? And so that's what the RU pooling is all about. We're able to pool across different accounts up to, we have also a node level governor. But on the local governor, what's happening is, historically, if we just use a shared nothing counter, we have a few different trade-offs, right? The benefit of having a shared nothing counter is, let's say if one node goes down, it's not a global rate limiter. I can go and continue to serve requests, and the system is highly resilient. But the trade-off here is, well, what happens if I'm overly spread thin across many replicas, many partitions, is all of these now also report into we call a global rate limiter, or we internally like to call it a controller service. And so think of it as a heartbeat where it's not on the critical path, where each of the local replicas is going and saying, hey, here's my utilization on how many RUs I am consuming, and here's the leftover budget that I have. All of that leftover budget is then sent over to the global rate limiter, where the global rate limiter on the response can also go heartbeat back saying, hey, you just used all of these RUs and you have some leftover budget. Meanwhile, this other partition's running hot, but because we have leftover budget somewhere else, let's say if this is the one that's running blazing hot, and this one's got leftover budget. What we're able to do is the global rate limiter can say, hey, let's relax some limits. I can give and donate some RUs back over to the other partition and help you pool that. And so these are some of the really cool new capabilities where we can give you leftover budget, give you higher burst ability, and do so in a responsible manner that still preserves a shared nothing architecture on the front door. Now, this is a lot to take in. Let me go and zoom out. We talked a little bit on partitioning, on replication, and on request units, on what happens behind the scenes in Cosmos DB. Let us know what you think about this format. If this works out for you, there's a lot of other topics we can do in the future, like indexing, the query engine, etc. Let us know in the comments on what you think, and please do fill out our form evaluations. Otherwise, thank you so much.
Thank you so much.
Thank you, Andrew. You know what's crazy is that that was such a great behind the scenes look. And you gave me something like this, I think maybe the first day I started on the team. So it's always great to kind of see this again. It's a refresher. Keeps me really up to speed on what we're doing.
Oh yeah. I mean, I figure we keep doing this as an onboarding thing internally, but honestly, it helps our developers so much when they know what's happening behind the scenes too, on rationalizing, hey, why is the system behaving the way it is? And that's the intent of also disclosing this out broadly here.
Fantastic. Well, thanks, Andrew. We appreciate it. And we now know a little bit more about how Azure Cosmos DB operates at scale. And you know what? We had so much information shared with us. And I want to go ahead and share some things that we've had from our community. Nicholas Chang, he's a really, really wonderful member of the global AI community, working to help get everybody. You might have seen him on one of these AI tours that we've got going right now. But he actually said that if Damian Brady, who's a buddy of mine who's over at GitHub in their DevRel, he said it was good to go, I think you should go. Patty, what else do we have as far as programming languages are concerned?
Yeah, we also released a poll about what programming language used the most, and it was great to hear that 45% of you developers use .NET. I personally am a Python developer, so I'm glad that I'm joined by 32% of the audience, and we're followed by JavaScript, TypeScript, and Java. So really exciting stuff. Thank you for filling out our poll.
Absolutely, we really, really appreciate it.
Yeah. But now we're moving into one of the most critical topics, which is data modeling.
Yeah, the decisions that you make early can define your application success. And it's a great reason to keep learning and sharpening your fundamentals. I know one of the things that I always hear from Andrew, who we just heard from, is making these decisions early are going to help you save yourself from headaches later.
No, 100%. Preparation really is key. And if you want to lock in those fundamentals, the Cloud Skills Challenge, again, it's a great follow-on. So data modeling is one of those topics. And again, it runs through May 8th.
Yeah, you complete the modules and you can enter to win one of 500 free DP420 exam certification vouchers. So start here at aka.ms/CosmosDB Conf Challenge. So next, we have an awesome talk from one of my favorite community champions, Hassan Savran.
Yeah, and we're going to be talking about data modeling decisions, Jay, and that they will make or break your Cosmos DB application. Let's go.
Hi, everyone. Hi, Azure Cosmos DB community. I am Hassan Savran. I have truly enjoyed meeting many of you at past conference, and I cannot wait to make new connections and talk about Cosmos DB at upcoming events. Today, I'm going to talk about the data modeling with you, and I'm going to try to make it interactive as much as I can. So I have no slides for you today. We are going to work on the VS Code as much as we can. And, we are going to actually look at the Stack Overflow data model and try to move it to Cosmos DB and make it scalable and very affordable. Currently, it's in the relational database, so we are going to take it from there and move it to Cosmos DB by using different VS Code extensions and tools. So I just want to kind of show you how I handle when I get a project like this. So I guess before we move to the VS Code, let's look at what we are doing, right? So we have limited time, so we cannot kind of look at all the Stack Overflow tables. So we are going to actually focus on the busiest part of the application, which is we display the questions, and we are going to go and click on a question and get all the answers, right? Sounds simple, but as you can see, there's all things are going on here. So we have like question, we have answers, we have comments, we have badges, we have votes. So we have, potentially a large application page to display here. So this is what we are going to tackle today. So let me go back to my VS Code, and let's start from the relational database where the data is actually currently at. So these are the tables we are going to tackle today. So we have the post table here. As you can see, there's a bunch of kind of like columns here. We have each post can have multiple comments and multiple votes. We have the user's information, and users can have number of badges. So in a relational database, you can easily join this table together and really deliver whatever the query is asking for. But we are going to go to the Cosmos DB, which we don't have any more joins. So what are we going to do? Well, before we jump, what we are going to do, let's talk about what we shouldn't do. We shouldn't just take this as it is and move it to Cosmos DB. This is not going to work because we don't have joins in the database side. So you have to kind of go and join each of these, data in your front end or in the middle layer, which is not going to be easy. So let me actually show you if we will actually take this as it is and put in Cosmos DB, what is going to happen. So I have a bunch of the different databases here. So what the application we are seeing here, this is the one that I created. It's available in VS Code extension. It's just for the Azure Cosmos DB community. It's free. You can download it. So what I'm doing here is I'm just picking my database. As you can see, all these tables that I just showed you, they are here available. So we are going to go and start with probably the posts table. So first, we have to go get the questions and answers. And the post table has both of them. So I'm just going to go and actually go click this one. Before I click the execute, actually, there's a good function here. So I'm just going to run my query analyzer here so I can track how much everything is costing to me later. So the first, we are going to go get the questions and answers. As you can see, it looks like we have 3. I'm guessing I have 1 question and 2 answers here. As you can see, it cost me 3 requests. Okay, not bad. But we are not done yet because we have many other stuff that we actually have to go and get, like comments. So to get the comments, we kind of need to use the in here because we are dealing with 3 objects, so we have to pass their post ID and get this information. So let's go and get that too. That cost me 337. Okay, not bad. But now we are going to continue. You might need to get the votes or maybe try to count the votes and display them on the page. So we need this information too. Another 3. Then, as you saw on the page, there are some user information. So I need to go and get the users for these questions and answers. I'm going to go and get those. Another 3 that I have to get paid for. Then I'm going to go and get the badges. I may need to maybe count the badges of each of these users, display emojis or whatever, depending on what they have. So I have to get that information too. Well, what's happening here? Looks like I have 277 badges, and it actually cost me 16 request minutes. So if I'm going to go back to my query analyzer, this is really what's happening. Just to display one page, I need to sum it up all these request units. I couldn't join any of this data in database level. So that's going to be, like my problem to solve in front end or in the middleware. So that's why you don't want to get a relational data model and move to Cosmos DB as it is. It's not going to be, a good for feature for today. As you can see, it's kind of as the data is going to get larger, if the traffic is going to get larger, it's going to get cost you more and more. So what do we do? Well, what do we do is pretty clear. We need to reduce the number of containers. So for that, let's actually look at this diagram here. That's where we are right now. We want to try to write and read data, but currently we have 5 containers. We only look at the read. We didn't even look at the write. So if I want to look at the write, I can quickly do that here. So let's actually try an update. So I'm going to just update a post. I'm just increasing those numbers here by using the patch operation. So let's see how much this is going to cost me. 15 requests. And that's only 1 container. So, things can get really expensive really quick with this. So as I said before, we want to, reduce these numbers, the number of the containers here. So what are we going to do here is, well, we have the post ID is the partition key in each of these containers, as you can see. Now, the good news is we have the post ID for getting shared by these 3 containers, and the user ID is getting shared by these 2. Since they share the same partition key, why don't we just put them in the same container, just like the version 2 suggests, right? So we have a post, our partition key is post ID, and each comments and votes is going to be under the same post document. Sounds good on paper. We can try it. Also, that applies to the users. So rather than we have 5 containers, we end up with 2 containers. So let's try that. Let's see how this is going to work. So I'm going to go and change my data model to 2 here. Go back to results. And as you can see, I have only 2 containers now. So let's start with the post. Well, for that, I'm going to run or execute the same exact query that I just ran. So let's see what's going to happen here. Execute this one. It cost me 3 request units. But this time I got all the information. I have the questions, I have the answers, I have the comments, and I have the votes. And if you look at the document size, 5.71. It's really not that bad. The good part is if I actually go scroll down, you're going to see everything is already mapped. So I know that these votes are for this question, these comments are for this question. So everything is really kind of ready to render in the front end. So I kind of like that. The next one, this is, I think, the answer. There's no votes and comments. Great. The third one, let's see what's going on here. Oh, that one kind of gives me some red alerts here. Why? Well, look at the number of comments we have, 21. So, which tells me the relationship between the post and comment is not one to few, it's one to many. Which means if comments are going to grow and we don't have a limit for it, then that means that we are going to have an issue in future for sure. This is great for today, but you really need to worry about the future too. When you start to have more data, more traffic comes into your databases. So I know this cost great, 3, but I don't think that this idea is going to actually work for this data model because in future, we will have issues. Well, let's look at the users table too. I guess that was the post. So this is my user table. Let's execute it. Let's see what's happening here. Again, 299. I have, looks like one user here. But look at these badges. I have 54 badges, which kind of tells me that maybe users can get the same badge multiple times. Then this is not going to be easy to kind of keep them under the one object like that. So this is a one-to-many relationship too, and really just doesn't make sense to me, especially for a feature to put them in the same place. Mainly because it's going to actually increase our data model, and there's going to be no limit for it. So if I'm going to actually go back to my diagram and try to maybe talk about the sizes. The size is important. As you can see, the data model size, you have a limit for it. 2 megabytes is the limit. It cannot be larger than that. And your data model, as long as your data model getting large and large, that means that your cost of the query is getting expensive and expensive. Same with the write cost, because Cosmos DB needs to handle many more properties, and it's gonna cost you more. So whenever you create a data model, you want to be give some kind of estimate how big this data model is gonna be. So if your data model is gonna continue growing and growing, probably you're going to hit that 2 megabyte limit, and your solution is going to get more expensive and more expensive every year as data grows and traffic grows. So because of that, yeah, it is a good kind of it gives me a good result right now, but for future, I don't think that I can end all this under the 2 documents or 2 containers. So what do we do? Well, one thing, we are going to roll back. But we really cannot roll back to that because it's not really cheap either. The good news is, well, we are still, I guess, sharing the same partition keys here. And I'm not sure if you notice one thing here. There is actually a nightmare here waiting to happen too. So if you look at our select statement, it says post ID is this number or parent ID is this number. So the first one is giving you the question. The second one is giving you the answers because both of them are actually in the same post table. The problem is the post ID is the partition key, parent ID is not. So as soon as, right now we have all data in one physical partition. As soon as you start to distribute this data, this query is going to become a cross-partition query, and it's going to get very expensive very quickly. So we need to do something about that too. So what do we do from here? Well, we can try the document type data modeling. Document type data modeling is working a bit different. So we still have 2 containers here, post documents and user documents. But rather than saving only one entity type in the one container, we want to save different types, and we want to control that with a new property named document type. So I can easily figure out which post is question, which post is answer by looking the post type ID. So I just change that and add question and answer document types in this post, so I can easily For example, when you click the question, that will be your question ID. And by knowing the question ID, I should be able to get all the questions, all the answers, all the comments, and all whatever really from this container. So this might actually work very well for the situation. Same with the users. You can just get the user information, or you can get the badge, or you can get all. And the other part that I really like about this one, this is open. So if you have different kind of document types later, you can continue adding here rather than creating new containers. So let's see how this is gonna work. I'm gonna go back to my Cosmos DB NoSQL Studio, change my data model to data model 4, and let's start with the post document first. Now, as you can see, I don't have the post ID anymore. My partition key is question ID. And if I want to get only the question for this, for example, question, I can run this and just execute this one here. And this will give me only the question, 2.94. Not bad. I can get only the answer here too. I'll execute this one, 296. As you can see, I have only the answers because there are 2 answers here. Or I can get everything. I don't care if it's a question, answer, comment. At the end, I need to render this in some way in my front end. So I can just do that and look at it. This is beautiful. You know what is beautiful? This is beautiful here. The cost is 3.61. And I was able to get everything, 29 items with that much request. So this is really very scalable and very affordable solution. I am really happy about this one. So as you can see, I have some answers here. I have some comments here. And you can easily look at the document type and render that in the correct places in the front end. Or if you want to kind of use a factory design and kind of put them in your the C# object or anything like that, you can do both. So this is working great. I'm really happy about this one. Now, next is usually developers will kind of stop here. Why? Because probably that was a requirement. Create a like a scalable, affordable data model, which we did, right? Well, I would suggest you not to stop there, because there's all kind of other things that you can still work on, and those are, what about the future? What is going to happen in the future? How can I make this data model better so it can tackle the problems that's going to come in the future for the system? So for that, there are a couple of options you can actually look at. The first thing I can look at is probably the tenants, right? So yeah, we have only Stack Overflow questions today. But as you know, Stack Overflow got much bigger. There's a Stack Exchange. You can actually take this, questions and answers and apply to different domains, and they can talk about the totally different questions and answers. So therefore, it will be a different UI, but in the back end, it will be the same. So we can really easily make that ready if we actually add the tenant ID to our data model. But we can do that. And if we are going to do that, then that means we can actually use the hierarchical partition key. Currently, we are using only regular partition key, which is the question ID. So if I'm going to do something like that, what is that going to look like? Well, all I need to do is I need to go and create a tenant ID in here. And whenever I'm asking the question here, I'm going to add the tenant ID 1, and question ID is this. So really, that's what my select statement is going to change into. And when I run that, it should run just fine. Let me go data model 5 first. As you can see, I have the data, so it's still 305. And if you actually go to Cosmos DB info tab here and look at the overall, so look at the partitioning here, my partition key is the tenant ID and question ID. So whenever actually I ask this question ID, let's say we have 2 tenants. One is about the C#, other one is maybe the farmers who's asking a question if how their chickens are can do better. So in this case, if you're gonna tenant ID 1, we are only search the C# question. We are not gonna search for farmers question in that case. So you can easily change the where they actually are looking by changing the tenant ID here. So I like this one. This will be actually make the system ready for multi-tenant systems. What else we can do? Next one is find questions. Now you're going to say, well, Hassan, this is great, but how are you going to find these questions, right? So the question is already in the page. You click on it, but users needs to find these questions in some way. So there are two things I will suggest for that. In older days, we used to have like categories. We used to have tags. Users supposed to go and click the category, find the products, what they need to find. But well, the things start change very quickly, right? So right now, everybody likes to chat. Everybody likes to write, what they need, and they're supposed to go and find whatever they are looking for. So for that case, what we can do here is Cosmos DB has two options that you can easily set up. The first one is full text search. In the full text search, all you have to do here is you have to go and look at your full text policies. You just need to define which language the data is in post body. That's where my data is. All that description about the questions or the answers. And I just create a full text index on with the post body. After that, after reindexing is done, all I have to do here is I can use the full text contains. That's one of the functions for full text. But this is one of the easiest one. So I'm looking for the questions. I'm looking the post body, and I'm looking for if it has any SQL server in the text. So if you can see, the post body is a pretty large text. So if I'm going to go run this one, and if the user goes and writes SQL server and search, this is what's going to happen. This is going to find top 10. And as you can see, the SQL server is in the post body out there. I'm just giving the title here. And the best part is, look at the cost. It really didn't cost us that much to make a search like that. Next one is the vector search. So the vector search, in that one, the user is really not looking specific words anymore. It's looking maybe like looking for a relational database operation problems, for example. So you have to go and find MySQL, PostgreSQL, and all kinds of stuff. So if that is the case, the first thing you need to do for that is you just need to create vectors. And as you can see, I created policies here. You just need to give some information about the model that you pick. And then this is my indexes. Interestingly, there's other actual options here, which I don't show it, but you can actually see in the Azure portal. That is the shard ID for the vector index. So in that case, we have tenant 1 and 2, right? So you can easily create those indexes, and the indexes will distribute it by the tenant ID. You can actually write that. So whenever you make the vector search, it can search only that tenant ID vectors. So it will make it much cheaper that way. And Discan is actually supporting that. So that's why I kind of like the Discan indexes. Anyway, before we go more details, I go more complex. Let's see. Also, this application is going to make the vector search much easier, because before you make the vector search, you need to generate the vector itself. So as you can see, if you have a vector policy, I have this vector search option here. You just need to go, and this is going to go and discover all the AI policies you have. And I have this embedding model, for example, and this is the data I want to vectorize or search for. Relational database performance issues. You click vectorize it. It calls and creates the embedding for you. You can actually easily see it here. So this is the text, and this is all that numbers is the vector I'm searching for. So I can easily use this embedding parameter. Before I click on running that, I hope you notice one thing here. Look at the document type. It is post vector. So I am not searching the whole database. I'm only searching for document type. So that actually makes my search much lighter. And I'm passing the tenant ID too, so I won't kind of go and search for farmer stuff, I guess, in this case. So click and execute. And this is going to cost a little bit more, because this is much more complex than looking for the word. As you can see, it finds MySQL, it finds SQL Designer, insert problems, dynamic SQL store procedures in Oracle. It's much more complex than the other one that I just showed, but it's available, and you can easily use that too. All right. The other three things that I can just talk quickly is schema version. You should have a property for the schema versioning out there, and every time the schema changes, you can just increase that. And you can use that property to, like if the business workflow changes from schema version to other schema version, you can actually handle that. Retention, you should really look into that because Cosmos DB should have only the hot data. If you don't care about that data anymore, you can just take it out and put it somewhere much cheaper. So that's going to make your data size smaller, and that's going to make your storage size much smaller, and things going to work much better. For that, you can use a TTL function of Cosmos DB. For example, if you don't care about the data after 2 years, well, you can easily make the TTL 2 years, and Cosmos DB automatically will delete your data after 2 years for free for you. So that will be a great thing to ask to all the the requirement, whoever give you the requirement, what is your retention policies for that. The last one is the analyzing data. We create a great operational database data model, but at the end, somebody needs to analyze this data. So you will see how the business is doing. So for that, Cosmos DB has the mirroring data to Fabric, and you can easily turn that on, and data analysts or BI developers can easily kind of go and look at the data and analyze the data and create reports from there. So those are the things that you should really kind of consider and think about in the data modeling side. Well, that's all I have for you today. I hope everybody learned something new today. If you have any questions, you can find me on the LinkedIn and Twitter or any other social media, social platforms, and I'll be more than happy to help you from those areas. Thank you, everyone. Thank you for coming to my session.
At the intersection of science, artistry, and design, Pantone gives designers, brands, and manufacturers a shared language to turn creative ideas into reality. I'm Sky Kelly, and I'm the president of Pantone. Going beyond color standards, Pantone is about the business of creativity and the trust and precision behind it. Pantone harnesses decades of research-based expertise and deep ties with the design community to understand and predict what's new and what's next in design. We really bring life to trends that shape culture. When Pantone and Microsoft teamed up, we built a system that translates those insights into actionable inspiration.
With the help of Azure AI Foundry, Azure Cosmos DB, and GitHub Copilot, we built AI agents that launch a new way to engage with our platform and instantly unlock our expertise. My name is Christian Risteski, and I work as a solution architect at Pantone. By combining decades of design research with the human insights of trend forecasters and color psychologists at the Pantone Color Institute, creative color palettes can now be delivered on demand to help guide design choices. The result speaks for themselves. GitHub Copilot saved the in-house development team at Pantone 134 hours over 7 months.
Color enthusiasts can mine years of research and insights in seconds instead of days. Foundry agents access, distill, and share color inspiration at scale. A business built on lasting relationships with the designers across the globe now reaches anyone who wants to unleash the power of color instantly.
What an incredible day. And you know what? You, the community, in our live chat, you've made it happen. We've heard so much from you. And so, Patty, why don't you tell me a little bit about some of the things people are doing today with AI agents?
Yeah, of course. So we just ran one final poll asking, where are you today with AI agents in your applications? And it seems like many of you, like myself, are still experimenting or building prototypes, while a lot of you, actually a surprising amount, are already building production workloads, which is amazing. Again, we are just entering the age of AI and agents, so it's always great to learn. And how about you, Jay? What do you have?
Well, you know what? We've been talking so much about community today, and we've heard from one of the members of our community, Jess Ramos, who does big data energy. She was kind enough to give us a little minute of her time. You might have seen it before. And of course, she gave us a little shout out. So Patty, I think it's about time.
I know, we've had a big day and we've heard from engineers, leaders building a real system at a global scale, and you.
I mean, I understand. It's been a long day.
It's been a long day.
Well, from AI applications to deep technical patterns with Azure Cosmos DB, we've learned so many things.
Yeah, and it's a lot to take in. So you can revisit every session, including exclusive on-demand content right here at aka.ms/CosmosDBConf26 playlist. And remember, the YouTube description has all the links from today.
That's right. And there are a lot of links in there. I'm going to make sure that you got everything you needed. And if you're ready to take the next step, try the Cloud Skills Challenge. Complete those modules by May 8th, and you can enter to win one of 500, you ready? Free DP420 certificate vouchers.
Yeah, so visit aka.ms/CosmosDBConf challenge if you want to learn more.
And so also, before you go today, please take a moment to share your feedback.
Yeah, you can find the evaluation form at aka.ms/CosmosDBConf 2026 survey. And we just want to make sure that we say thank you to some of the people that made the event as amazing as it was.
Yeah, you know, I've been doing this event for a few years, and there are always so many people who are behind the scenes that we want to show some appreciation for. So I want to say, first and foremost, Mikal, you are one of the reasons I am able to bring this together every year. Love you to death. Sarah and Bill at Catalysis, every time we do this, we succeed. And they are two key parts of this. Everybody from Run Studios, you did a great job. I'm so thankful for all the support we've been given. The team from the Reactor, and of course, the community, all of you.
Yeah, and I want to thank the amazing speakers, sponsors, audience, and the team behind Cosmos DB and this conference. And well, that includes you, Jay.
Aw, thanks, Patty. You know, I had such a great time hosting with you. I'm so glad I'm here. And while I've been here, we've learned so much. And now we have the ability to build something new.
Or you can use some of our best practices to improve what you might already be building with Azure Cosmos DB. Jay, I had a blast working with you.
And you know what? Of course I did too. You know what? Doing this event, it really makes me realize how much I always have to learn more about Azure Cosmos DB, or now Document DB.
Yeah.
I've got so much more to learn, but I need to get to it. And so I'm looking at my watch, and you know, it's time to go.
Wow. Thank you so much for spending time with us, and we'll see you next time.
Love y'all. Bye-bye.
Thank you for joining us.
Thank you.
Thank you.
Thank you.
We'll see you next year.
Thank you.
Thank you for being a part of Azure Cosmos DB Conference 2026.
Thank you.
Thank you.
Thank you.
Thank you.
We'll see you next year.
Thank you.
Thank you. Thanks for joining us for Azure Cosmos DB 2026. We'll see you next year.